Okay, welcome back, folks, to the second session of this day. And the first talk of this session is by Anna Shapere, and her talk is about time crystallinity in open quantum systems. Go ahead, Anna.
Thank you. So let me share the screen. Yeah, thank you very much. I want to thank, first of all, the organizing of this conference, which is a very nice conference. I have to say that I'm not a person which is very expertise in time crystals, but we got interested on it because we were working in open quantum systems. So let me first tell you who is the team. So this work, it's mostly and has to be granted to Andreu Riera Campagne, which is, he's doing the PhD with me. And he's the person who was really digging into this problem. And we have a lot of help from Mariona Moreno Cardonet, which is a postdoc at that time on my group, and that she's an expertise in open quantum systems. So as I say, I am not an expertise on the field, but we were wondering what was these time crystals when we were talking about open systems. And so there was two questions that was for us important. First of all, it's how to define a time crystal in an open system, because we found nice definitions for closed systems, but when we were digging into the literature to understand what was in an open system, that was not clear, if there is a clear definition. And second question that we were interested in is that at that time, most of the time crystals that they were presented in open systems, they were always using mean field or long-range interactions. And we were wondering, first of all, if that was needed. So, and also which physics can be put under the carpet when one uses mean field, because which part it's classical, which part it's quantum. So I'm going to present this talk a little bit in the backwards direction. First, I want to give the results, because the thing that we did is a little bit technical and I don't want to enter into that. So I don't know if I will reach time to explain a little bit this technical part, which is not so important. But then I want to explain and to talk, which is very related to the previous talks, very nice talks by Masahito Ueda and Hemmerich about the difference between Lindbladians and Hamiltonians. And finally, I will explain how do you treat these periodically driven systems and what is this battle against decoherence. So when we were searching in the literature, we found pretty nice definitions of what a discrete time crystal, I'm only going to talk about discrete time crystals, in a closed system is. And say that if you have a closed system, a discrete time crystal is characterized by an observable, which acts as an order parameter of your system and whose expectation value fulfills three conditions. First of all, it has a time translational symmetry breaking. So although the Hamiltonian is periodic on time, this order parameter, it has not the same periodicity of the Hamiltonian. It has a periodicity which is n times the period, and this n is larger than 1. And then there is a rigidity of the oscillations. So this order parameter has to show fixed oscillations at the required period, even if without a fine-tuned Hamiltonian parameters, because we understand that that will distinguish between having a critical point, but if this is a phase of matter, it has to be stable, so it has to have some breadth, so it cannot depend strictly on the fine-tuned Hamiltonian. And finally, it has to have persistence to infinite time. So these non-trivial oscillations with this periodicity have to survive in the thermodynamic limit. So if we want to go from, well, let me present the results and then I will explain how did we reach. So our idea was, first of all, we wanted to propose, because we were not satisfied with the definition, so we couldn't find a good definition of what a discrete time crystal should be in an open system. So we wanted to define what it is and to characterize it using Lindblad equations. Then in order to do that, what we show and we propose is a proposition that there is a key element, which is the Floquet propagator, which defines what a discrete time crystal must be. And this Floquet propagator obviously depends on the properties of the Lindblad. So we wanted to dig into the Lindblad physics to understand which properties can bring to a time crystal. And then finally, the other question that we wanted to show results were that there is not need to have a mean field or long-range interactions. This is not needed. However, when we talk about the Lindbladians, we saw that there is a difference between having collective jump operators or individual jump operators. So let me show what is the physics behind or the comparison or how we learn it, right? Probably it's known by many of you, but for the ones that they are not used to work in open systems, let me show these different things. So when we have a system plus an environment, normally if we have Hamiltonian dynamics, we assume that the environment is the couple from the system and describe all the dynamics versus with a Hamiltonian, which we know that they use for isolated systems and has a unitary dynamics. They generate a completely positive trace preserving map as they should be. And we know that if we want to have physics which is exotic, what we have to do is to engineer in the Hamiltonian parameters. And in this way, we can drive our system to, if the Hamiltonian is a little bit complex, or at least has two terms in order that there is some kind of competition. And if we engineer in the Hamiltonian, we can have very exotic phases of matter. Okay, and often these phases of matter are linked to the fact that we have more than one ground state, or linked to the fact that we have gapless, okay, transitions, and then there is correlations, and some of these things happen. So the degeneracy of the ground state is quite an ingredient, important ingredient. On the contrary, if we use Lindbladians, what we are doing is we are assuming that the system is in contact with an environment, and we have to describe the system as a result of the Hamiltonian dynamics of the system has plus the interaction with the path. So Lindbladians are used to describe decay and decoherence in quantum systems which are induced by an environment. Of course, they also generate a completely positive trace preserved map, which is a very nice thing. And this is the reason that although these Lindbladians have been proposed many years ago, much before Lindblad indeed. So it was later when it was shown that this is a completely positive trace preserving map. And now we have the possibility also to engineering the environment. And if we engineering the environment, we can change also the properties of the system. And we can also go to these exotic phases of matter. And we know that in these cases, very often, it requires that the Lindbladian has more than one steady state. So there is a kind of equivalence between these two things. Okay, but there are some things which are very different, and we have a talk today that it was showing. Hamiltonians are Hermitian, Lindbladians preserve Hermiticity, but they are not Hermitian. They can be diagonalized, and this is the way how we know how to deal with Hamiltonians. We diagonalize the Hamiltonians, and then the evolution we know that corresponds to the eigenstates of the Hamiltonian if the Hamiltonian is time independent, and we have the evolution equations, and we know that symmetries, they bring conserved quantities. In the Lindbladian, this is a little bit different because sometimes they cannot be diagonalized, but I'm not going to talk on these cases, which one can solve. And the evolution is given by this typical master equation. And they also conserve quantities of evolution, but they are not linked to the symmetries in the same way. And this is an important ingredient. And as we have seen today, Lindbladians are used for a lot of things, in particularly, as it was in the talking this morning, to study non-Hermitian systems. So how is this Lindbladian? So, well, this is the master equation. And what I want to show in this master equation, of course, we know there is a first part, which is the von Neumann equation with the Hamiltonian system. So if we don't have jump operators, that will be the unitary dynamics. And then we have this expression of the Lindbladians, in which the important part I want to remark here is this kind of sandwich jump operator. Okay, this is the thing that forces us to use density matrices, and it cannot be written for a pure state because the phasing makes that the system evolves to a density matrix. And this Lindbladian can be grouped in a pair, which is a non-Hermitian Hamiltonian. This is the physics that it was today Masahito talking, plus this sandwich operator. Okay, so Lindbladians preserve Hermiticity, but they are not Hermitian, and they generate an evolution map, which is this epsilon of t, okay, which is the exponential of the Lindbladian. And we know that this map, if the Lindbladian is Markovian, can be decomposed in this way. and we want to understand the physics in the same way that we do with a Hamiltonian, diagonalizing the Lindbladians. And how do we diagonalize the Lindbladians? Well, there are more technical ways to do it, but the way to diagonalize a Lindbladian is to use a matrix representation of a Lindbladian. I mean, if you look in this equation, you see that this is not a matrix, okay? So we cannot diagonalize this Lindbladian directly. And this is a technical thing, but a very useful and very simple once, like everything, once you learn how to do it. So what does it mean to do vectorization? Well, we know that the operators, they are also a vectorial space. So what we do is writing the operators, which normally are written as a matrix, as a vector. That means if I have a matrix, which is n by n, I reconvert this matrix in a single vector, which has components n squared. It's a single column. And what is important is to see how the operators act in this case, and in particularly how the sandwich operator acts. And this sandwich operator acts in this recipe. So if I have an operator A acting over my density matrix time B, when I vectorize that, this is a tensorial product of A times B transpose. This is important because this is how I have vectorized on my vector density matrix. Now my density matrix is a vector of components n squared. So if I have a Hilbert space of dimension n, the density matrix is just a column vector which has n squared components, and the Lindbladian it's a matrix now which has dimension n squared times n squared. And this is very nice, but also makes some problems when one tries to diagonalize it. Okay, so now if we want, assuming that the Lindbladian can be diagonalized, we diagonalize it, but since this is non-Hermitian, and this we saw it also this morning, normally or always it has different left and right eigenvalues. Okay, so when I diagonalize my matrix, I have an expression of the Lindbladian which some eigenvalues, lambda mu, and eigenvectors, which again, these are matrices written as a vector, right and left. And if I'm able to diagonalize my Lindbladian, and the Lindbladian doesn't depend on time, I can immediately see how is the time evolution, because when I apply my Lindbladian to an initial state, I will have that the evolution is like the projection of my Lindbladian on the initial state, of course, with an exponential, which will be the eigenvalues of the Lindbladian. So now, if we want to understand if we want to understand the physics, one way to go is really to dig with a little bit of heart into this Lindbladian and to see what are the characteristics of the spectrum of the Lindbladian. So the eigenvalues of the Lindbladian are either real or come by conjugate pairs, because we know that the Lindbladian is non-Hermitian. We expect that it will be also, they will have complex eigenvalues as it has. But since the Lindbladian or the associated map, it's positive because it has to be a physical map, that means that the eigenvalues, that they have a real part, the real part has to be negative. Yeah. And then if we form the evolution map in this way, so we have a map which is just the exponential of times the Lindbladian, we see that the Lindbladian and the map, the generator map, have to share the same left and right eigenvalues and also the eigenvectors. And now we know also that for any time-independent Lindbladian, there is always one eigenvalue which is equal to 0. Okay, and if we plot that in our time evolution in the map, we see that the right eigenvalue it's a steady state, and the left eigenvector corresponds to the identity. It's a steady state, although this is a little bit wrong. It's not really a steady state because it can have a phase, but we will call it that this is an asymptotic space. And it can be other states that they don't decay in this way. And this is what we were going to call the asymptotic superspace of the Lindbladian. So this is formed by all the right eigenvectors of my Lindbladian such that the real part of the eigenvalue is equal to 0. One has to take into account that when we do that, the span of these right eigenvectors, maybe they are not density matrices. They don't have to be physical. Some of them can be, some of them they cannot be. So if we know that, okay, we can classify, I have plot here where I have taken from typical plot how is more or less this spectrum. Okay, and this spectrum, we see that we have in the real part, this starts at 0, we have some eigenvalues which they have 0 real part and imaginary part, and then there is something which is very important that we call the dissipative gap, which is at which distance, okay, which is the difference between the real part of the eigenvalues, the minimum of this distance, because this dissipative gap which tell us how the system decays. So if we have a dissipative gap which is very high, very big, the system will be stable in order to decay. Okay, but if it's very small, it will decay. So the important thing, and that will be fundamental to have a time crystal, is that we have to have an asymptotic space whose dimension is larger than 1. So, and now I say that there is also a big difference between Lindbladians and Hamiltonians, which are the conserved quantities. And what we can see is that essentially for each state of the asymptotic superspace, which has only imaginary eigenvalues, there is a conserved quantity. And this conserved quantity tells us that the evolution of the state, if we plug now our Lindbladian here, we see that the evolution of this state is of the following form. It's a linear combination of the asymptotic spaces with a phase, which depends is the imaginary phase of the eigenvalues of the asymptotic space times the conserved quantity. And the other terms, they are of the order minus the gap times the dissipative gap times the time. That means for time going to infinite, this order can be out. Which these things in our hands, now we can go through the Floquet propagator. Okay? And now if we have a time periodic evolution, so we have a Lindbladian whose dependence on time is periodic, we can define the Floquet propagator, which for us is going to be the most important quantity. And the Floquet propagator, it's like always, is expressed because now our Lindbladian has a time dependence, so it has to be time order, it's the exponential of the integral of the Lindbladian over a period. And this Floquet propagator, it's time independent. So it doesn't depend on the properties that the Lindbladian has at a given time t. And this time propagator, we can also vectorize it. Okay, and we can vectorize it and we can find also that it has left and right eigenvalues. And since this is non-Hermitian thing, the conjugated, which is here written like a double dagger because it's not what we understand by the conjugate, corresponds to the left eigenvalues, and the right eigenvalues gives us the right eigenvectors gives us the right epsilon mu, which is the eigenvalue times the eigenvector. And we can define now also which is the asymptotic space of this Floquet propagator. And that will be spanned by all the right eigenvectors that they have modulus 1 eigenvalue. Okay. And well, if you look, this is very similar to what we found before, because we were asking that the asymptotic superspace of the Lindbladian, it's formed by those eigenvectors that they have eigenvalue real part equal to 0. So when we exponentialize that, that means that the eigenvalue has to have modulus 1. And this, with this construction, we can separate our map into two parts. There is an asymptotic part and there is the decoherence part. And these two guys, they live in different superspaces and they are not connected. So time crystals, we appear only if we have asymptotic space which is big enough. So this has to have dimension 2. So once we have that, now we can define what is a time crystal. So if we take the Floquet propagator, which is the map, which is the evolution map in a dissipative system under a periodic drive, we can define or we can identify that a many-body quantum system will behave as an open time discrete time crystal if the Floquet propagator fulfills the following. First of all, it has a time translational symmetry breaking. And now we are not going to talk about an operator, but we are going to talk about the eigenvalues of the Lindbladian. So it must exist at least one eigenvalue, which I denoted by epsilon star, which is not 1. So it's not the corresponding to the lowest eigenvalues, but has to fulfill that this eigenvalue, when it's exponential to a time n, will be equal to 1. And that will give me the periodicity of the time crystal. So this is the first condition. It's equivalent, or it will revert in having one observable, which is periodic on time with different periodicity than the driving. Second, what doesn't mean rigidity of the oscillation? Be robust, and we demand that it's linearly robust. So if our Floquet propagator changes by some kind of eta times an operator, then we use that the susceptibility, which is the derivative of this value of the Floquet eigenvalue versus this changing or perturbation, has to be equal to 0. Of course, one can say that in order to have rigidity, one should be invariant under any order, so not only linear order. But here we are studying, because it's very difficult, if not, what happens, what is the linear response of our system in front of a perturbation. And finally, we have to say what are persistence. What doesn't mean the persistence of the oscillations to infinite time? Well, the persistence of the oscillations to infinite time here will be that we have a Floquet gap, okay, which is of the following way. So it has to be like the logarithm of this eigenvalue of the Floquet operator divided by 1/t. If the Floquet time, the Floquet gap closes, the system will be stable. Okay, so what we have done with this definition of what we believe defines what it's a time crystal in an open system, we have tried for different systems, very simple systems and very complicated one. Yes. So I will go only to the complicated one, and in the case typically in which we have that the time crystal which has periodicity 2t. In this case, we have to have 2, okay, because this is the periodicity, two states in the asymptotic space which fulfill, first of all, the one which always happens because any Lindbladian has a stationary state, epsilon 0 equal to 1, and another one, the star, which will be e to the I pi, which of course, when we square it will give us the identity. And the evolution, well, the evolution, if we know how are the stationary states and we know how are the conserved quantities, we obtain it immediately. And then if we take an operator, and this operator will be the trace of the operator over the Floquet, propagator, we will find that this operator reflects all these qualities of the time crystal. So what is the way? The way is, first of all, we have a system. So we have to find which are the asymptotic states and the corresponding conserved quantities. Then we have to study how is the superharmonic response of the protocol, which will be a kick protocol. And then we have to study which is the rigidity of the oscillations. And if we do that, we will see if we have a time crystal or not. So what we did is we took a system which is a short range interactions, XY model. This is the phase. I don't want to go into details. This is quite technical, but the first thing that we had to do is to derive the microscopic master equation. And when we derive the microscopic master equation, we find that we have two kinds of evolutions. One corresponds to collective jumps. That means the whole system reacts to the environment collectively. And the other one has independent jump operators. That means that each of the spins that are in our chain reacts independently to the bath environment. And these two, collective and independent jump operators, appears in different phases of the phase diagram, because it depends on how is the energy distribution of the many body system. But when we do that with this definition, we look for the three properties of the time crystal: symmetry breaking, rigidity, and persistence. So here are the results that I wanted to show you. So we take this XY model, and first of all, we look we look for the magnetization, will be our order parameter. We know how is the asymptotic space. We found that there is in the kick protocol that we put, we have two states which live in the asymptotic space. This is the first condition to have a time crystal. We look at the superharmonic response, so how are the oscillations of the magnetization along the x-axis, and we see that for different perturbations, and we see that in some phases of the, in some parts of the phase diagram, they are very stable. This is the first plot, and now we look for the robustness and for the Floquet graph. And this allows us to distinguish what phases are time crystals and which phases are not. So when we look for the robustness, we put an interaction and a perturbation on our kick protocol, right? And now we look which is the response of the system. And we see that there is some responses which is 0, so the system is very robust, and this is what we call a time crystal. And we see that they are, when we increase the perturbation, and also depending on the phase, on the part of the phase diagram of the model, we find that our system evolves towards a thermal state. And this distinguishes between a time crystal and a thermal. And finally, we look for the Floquet gap, which has to be quite coherent, which what we find with the robustness. And we see that the Floquet gap, it tends to infinite, so there is no dissipation in the time crystal, while it closes and brings dissipation and thermalizes outside of the time crystal. And with that, I would like to thank you to finish, and thank you very much.
Thanks, Anna.
Yes.
So are there questions? The superharmonic response in your results is this interference pattern that I see, or is it?
No, it's because there is many plots put it here together, and
the period is 10 or something like that?
Yes, yes.
Okay.
Yeah.
It's hard to see.
It's hard to see, yes, yes. But it's because we wanted to go to very long periods in order to show that this really, it's robust. Okay, so it's kind of in the thermodynamic limit. I have to say the thermodynamic limit here, it's very small, because diagonalizing Liouvillean, it's very expensive. So,
Rosario.
Yeah, so thank you. I wanted to ask you if you think there is any relation between this type of, this definition of time crystal in dissipative system and, those things that were done in noiseless subsystems or decoherence-free subspaces.
well, yes, yes, of course.
Can you comment on this, please?
There is a relation, because the asymptotic superspace includes the decoherence free superspace. Okay, so this is clear. So although it's not necessarily the same. Okay, so but when, especially in all these protocols in quantum information, you want to preserve quantum information when there is noise, you want to be in the coherence free superspace. Here there is something related also, because I have to say that what we have found is that short range interactions allow to have a time crystal, but the nature of the collective interactions dissipation is important. And this is important because these collective jump operators tends to preserve coherence, while individual jump operators tends to kill the coherence. And this is why one has to study which are the conserved quantities, and the conserved quantities depends on the form of the Liouvillean. So what we found, it's not important to have long-range interactions, mean field, that doesn't matter, it's not relevant. But if you don't have it, you have to have stability is much helped by collective jump operators.
Okay, we have time for one short question from Shane.
Yeah, I was wondering, what was this condition on the gap, on the dissipative gap? I didn't understand that.
Yeah, the dissipative gap tells you that, so a priori when you have a Lindbladian, you have two things, no? You have the coherence and dissipation. Yeah? So the dissipation gaps tells you how much you dissipate towards another state. Okay, so if your dissipation gap is very small, okay, the stability of your system is small. If the dissipation gap is big, it takes an effort to the system to go to dissipate to other states. So you would like to have normally, I mean, the Lindbladians are kind of, for me, very magical, no? Because if you look at the Lindbladian like Masahito was looking, so there is a part which is a non-Hermitian Hamiltonian, and this non-Hermitian Hamiltonian, it's deterministic. Okay, so it acts. So what? So it's acting there and so on, and creates all this dissipation. So in some way, if you only have this part, what happens is that the map, it's not trace preserving and completely positive. And then you have these jump operators, the sandwich jump operators, which makes all these crazy things that in some way you can understand that helps the map to be still completely positive and a physical map. So these two things, they go together. So they are not completely separated. So this is the reason one cannot study only the first part, right? Because if you only study strictly without putting the jump operators, your dynamics will be non-Hermitian, but it will be non-positive trace preserving. So it will never be a physical map.
So I thought the gap is
I think we are out of time, and you can talk in private. We thank Anna again, and the next talk will be presented by Hamir, dissipative phase diagram of a periodically driven quantum many-body optics platform. Hamir, can you unmute? Or can someone unmute Hamir? Rosario?
Yeah, I think I did it.
Thank you so much.
Okay,
Yeah.
good.
Now this worked out. Okay, so let me start thanking the organizers for having paved the way to my talk. So basically, I don't have to say what is a time crystal. I don't have to talk about dissipation because all the speakers did it in advance very carefully and very well. And in addition, I can rely on what Anna said before. So I'm not an expert on time crystals. I do for butter and bread, a study of non-equilibrium phase transitions, but in some sense, this project I'm going to talk about is something that motivated me to do my usual work inspired by dissipative time crystals that are the topic of this morning session. So when we started to look and think about this stuff, the state of the art was relatively, let's say, still at its infancy. So people were asking a very reasonable question, which is, can I counteract, for instance, in pre-thermal time crystals, the heating, the Floquet heating, by cooling the system with a cold bath? And this was a sketch that most of you know from this influential work by Bauer, Els, and Nayak. And of course, at the same time, there were very reasonable statements like, okay, come on, if you exaggerate with dissipation, you are going anyway to destroy the time crystal. So how can really dissipation help in such context? As you by now all know, or if you don't, you will discover in the course of today's talks, basically just 1 year later, Sao and Fernando had this idea to suggest using a very simple and toy model, dissipation can cook up a time crystal, and then later on, all the machinery of dissipative state preparation came at full force. And these are a few people that, as you know, already contributed to that. So I want to say that my talk, although talks about dissipation, is going to be in between. So I'm going to drive light matter interactions. So I'm going to do a Floquet drive, and I will use photon losses in order to stabilize a driven dissipative steady state. So I want, in some sense, good contractive dynamics that will bring me there no matter from what initial condition I start with. So in this sense, it's a little bit in between of the two stories. But maybe the true alert that you should keep in mind is that in my talk, many bad interactions will have an unusual role. So normally in discrete time crystals, they stabilize. They are essentially used in order to entail the superharmonic response. In my talk, they are going to have a destabilizing role. And that's probably one of the major differences. I have to say that if you have taken due consideration to the last slides by the talk of Andreas Emmerich, essentially you've seen already there that by increasing these two-body collisions, there can start to be a displacement for the period doubling. You can start to dephase from that. So you are in some sense already mentally prepared. So depending on the familiarity that you have with the review by Norman Company, Basically, that's the current zoology of time crystals. And mostly your favorite examples lay in this part of the table. And this is what we covered yesterday. Today, we are going essentially in the bottom part of the table. If you scroll it down, you're going to see that they talk about large N models or Dickey models. And they mention a fine tuning. And I want to explore a little bit what this fine tuning means. That's, after all, the content of my talk. So the model starts with an inspiration from a paper by Masahito. And basically, it's the old-fashioned Dickey model. Nothing particularly fancy so far. So you're periodically driving light matter coupling. So the Dickey model, for those that don't know it, is just the Ising model of quantum optics. You put a bunch of spins inside of a cavity. There is one just single photonic mode inside of the cavity, and the photon can be lossy. And you periodically drive light matter coupling in a way that I'm going to discuss in a second. So your problem is a problem of several spins that are collected in this gigantic S. This is just the sum of array of every individual spin. And if you don't know, you see it now, a strong light matter coupling, you have an SSB of a discrete symmetry. As I said, is an Ising model of quantum optics. So there is this parity operator that is a good symmetry of your Hamiltonian, but you can get to degenerate ground states if lambda is greater than lambda critical. This reflects, of course, if you look for steady states of this problem. So if you do a quench and you have losses, or if you periodically drive, this was known already, I think, since 10 years now in some pioneering work by Simons and Killing. But what we are going to do here, and this is still belonging, let's say, to the preparatory work to the core of my talk, this is what the group of Weda they did. They alternate a bright and dark cycle. So basically, in every period T, you're gonna switch on and off light matter interactions. You're gonna pick up lambda inside the super-radiant phase transition. And you're gonna, in particular, to select, in a first instance, your frequency of photon and of the spins to be in resonance with the frequency of the drive, such that when you switch on interactions and your dynamics is trivial because just you have the quadratic part, you can basically, when they are in resonance, implement the parity swap. And so this results in the fact that alternating bright and dark cycles, you are going to end up into a steady state with different parity only after twice of the period. Now, what is the question that usually I pursue in my research is to ask whether there are some genuine many-body non-equilibrium phases of matter. And the reason why I'm stressing many-body here, although several of you could still think that this model is many-bodish, is that essentially the Dickey model, if you don't add interactions that are these ones in red, you can do it, of course, in many ways. But the Dickey model, plain and simple as you get it in a textbook, is exactly solvable on mean field. So a large N, you get a gigantic spin, its quantum nature is completely eradicated, and you just have to solve the classical equation of motion for coherent photon amplitude and for the two angles of this large spin. In other words, if you want to do a quantum simulation of finite N, this is not so much expensive because you have this permutational symmetry starting from the fact that every single atom indistinguishably couples in the same way to the photon. But when you add interactions, when you break this permutational symmetry in the Hamiltonian and you introduce, for instance, a short range Ising type interaction, then you can't benefit anymore of this exact mean field solvability. And here you start to have troubles. You start with troubles because you are working now with a periodically driven problem. There is dissipation. So as Anna was pointing out, numerics is expensive, and you have to deal with true many-body interactions. You have to take care of the fact that you are not driving anymore a classical problem, but essentially the spin waves or any other type of excitations this channel is going to build up, they will be fed by this continuous pump of energy, and the system can eat up, in principle, to infinite temperature, even if you have a little bit of losses. So if you want, the question basically here is, are there genuine many-body dynamical phases of matter in this problem? What happens when we add J to the Dickey time crystal that Masahito worked out a couple of years ago? And one reason why I decided to pick up this specific topic is that essentially, as you have seen a couple of hours ago, and as I discovered in December, essentially the group of Andreas took inspiration from these works on decay time crystals and did the experiment. You have seen it recently. There is nothing to add about it in case people connected just now to the conference. All right, so I like to go to results first and then talk about methods. So one word about methods so you understand what I'm showing and the reliability of what I'm showing. I'm doing a self-consistent dynamical spin wave theory. So I am decomposing the many-body interactions in spin waves, but equilibrium spin wave theory will break down. So I do a self-consistent loop between the motion of the collective spin and the spin waves that will be generated by the J term. How this works, I'm going to tell you later. What you need to check is that at the time at which I'm showing you the plots, the density of spin waves remains small. If this happens, not shown yet, then you can trust the results. These are your first, let's say, shoot at your dynamical phases. I have on the y-axis dissipation and the horizontal axis many-body interactions in units of the frequency of the drive that therefore doesn't play any role. And basically, you can see a couple of behaviors that you expect. First and foremost, I introduce you this decay TC that essentially is in essence the same that Masaito was finding. And it is a very old-fashioned period doubling in the form that all of you have seen so far. So nothing, let's say, to comment about that. There is, of course, a region in which you don't have any dynamical order. It's just a mess. These points are stroboscopic points on the block sphere for the trajectory of your collective order parameter. You have to imagine that now, though, you have a finite J. So the motion of the collective order parameter has an internal bath of excitations, or spin waves, generated by the J term. And what can happen is that at a certain point, when you exaggerate with dissipation, with interactions, J, but you don't have enough dissipation, you might end up heating. Essentially, you are not counterbalancing enough your periodic drive, and you're going to heat up at infinite temperature. To be very frank, this heating region with H here are essentially a region where we don't know where the problem is going because our method breaks down. So this H is more something like in Latin, hic sunt leones, you can't go there, there are lions. We don't know, but as all of you in this conference are aware of, solving a driven dissipated many-body problem is challenging. So we will, let's say, think about other methods for the future in this part of the phase diagram. And of course, I agree with you that probably also this limit is in some sense expected. If you overdamp your problem, you're just going to get again some sort of boring relaxation. This is overdamping. Perhaps if we still, let's say, confine ourselves as small j, observations here are that you distinguish these transitions with different order parameters. Here, what you have is a broadening of the Fourier signal that goes from being sharp, like in a time crystal, to something more sparse, as you would expect for a signal like that. While here, instead, I'm using essentially SX. So what's going on by intuition, so why bothering writing a paper? There is an appetizer, and then there is a main dish. And the appetizer is this metastable time crystal. This metastable time crystal, as you're going to see, is essentially a very long-lived period doubling before collapsing into an overdamped situation. So somehow interpolates from the phase from which it comes from into the phase where it ends. So I'm going to talk about it, and let's say, recapitulate therefore, that if you don't have spin-spin interactions, if you don't have J, the regime in which you heat up a lot of spin waves is going to disappear. That's natural. But also this metastable time crystal will not appear. And this is what I'm going to show you in the next slide. So that's an ugly picture on how your collective order parameters look like if essentially you are going a very long time. And it's ugly because I want to show you that there is a damping. There is essentially basically a very slow decaying envelope. And if you look, though, essentially at some short time window, you can figure out that the signal is damped. You're going to have this period doubling, and you're going to not find any difference from what I was showing you before. That's why I'm portraying here these huge time scales. And this happens, of course, at every, let's say, interval, at each interval of time that you are portraying. So you will always see this period doubling. Now questioning what provokes the metastable dissipative time crystal. And let's start from saying what is not first. It is not a perturbative phenomenon. It starts at finite j, small but finite j. It is destroyed by many-body interactions. So it's certainly, this makes sense from the way in which I'm building my discussion, but maybe more importantly, for those of you that are familiar with perthermalization in Floquet problems, this is not the result of a high frequency expansion. That's not the theorem by Dima and company. Frequency is just an overall energy scale in such a case. So if you look more closely at your key quantities that are the spin wave density and, for instance, what the photon is doing, you can see that at a certain point, there starts to be a motion encounter phase between the photon number and the spin wave density. And as you will see later, they actually couple to each other when you solve your equations of motion. So probably the fact that they keep some sort of antiphase is the reason that you get slowly out of resonance. And this is going to kill your metastable time crystal. If you're wondering whether, let's say, these transitions here are sharp or not, well, again, this is not an order parameter, certainly, but spin wave density is having a sharp jump at the onset of the MTC. So probably there is really, let's say, something substantial happening there. Also, the lifetime immediately feels that you are switching on many-body interactions. So this is for the aficionados that like to ask the question, how long time it lives. That's roughly what is happening as a function of J for the lifetime. Okay, so let me say that if this was, again, I mean, I like, to build and to drive you for the same way in which we went for this project. Again, if this phase diagram here was the end of the story, basically you could tell, well, your method maybe is not in the essence perturbative, but the results are perturbative. And what I'm going to show you now, that if you play with the sign of J, if you play with the sign of your many-body interactions, you can get a strong coupling driven dissipative time crystal when J is negative. Basically, now this scale is maybe a little bit exaggerated. What I'm trying to say here is that there are regions, not fine-tuned point, there are regions of finite dissipation with J negative, where you get essentially, again, this decay time crystal. So I'm not going to show you, again, the plots. They look all the same. And my point is that what is happening is you have changed it from anti-ferromagnetic to ferromagnetic spin wave scattering. And as I told you at the beginning, the decay time crystal would like to favor a sort of ferromagnetism in the cavity. So if your true many-body collisions have the same notion of order, they're going actually to give you resilience to many-body heating, and they will not fight it. And in some sense, right, that's probably the most relevant part is a non-perturbative, driven dissipative phase of matter that lasts very long. And if you want to see what happens to your spin wave density, that's a figure of merit. So I remember you that the collective order parameter that I'm plotting for the decay TC is self-consistently coupled to your BEF of Gaussian spin waves. And you want essentially to be sure that your density of spin waves doesn't go too much. It's normalized to 1. And what you should appreciate here is that by changing of 1 order of magnitude from anti to ferromagnet, you can get a drop of, let's say, a significant drop of a factor 2 in the renormalized spin wave density. So this would be essentially already a signal of the fact that you are heating up too much. This is instead telling you that you are behaving similarly to what you will got here at very tiny J, but anti-ferromagnetic. So that's if you want a quantitative statement besides just showing you a cartoon of what is going on. And basically, now depending on time, I would appreciate if the host can tell me how many minutes do I have still?
7.
7 minutes. Very good. I can talk about the method, which is relevant to understand how you can trust this entire picture. So that's just a rewriting of the model, maybe a little bit messy. What I want to clarify is that we are decoupling our spin system into the motion of the collective order parameters, so basically this big S, and then we decompose these short-range interactions into a BEF of spin wave. As I told you, they are self-consistently coupled, and I'm going to show you the equations and details of the derivation in a moment. And they generate, if you want, a sort of internal BEF quantum fluctuation for the order parameter. So you are getting quantum noise and quantum and spin wave scattering from this J term, but at the same time, the order parameter has to deal with another BEF, that is the photon that is cold. And it talks intermittently to the photon, right? Because as I told you, this lambda t switches from bright to dark cycles. So the order parameter has to compromise essentially between these two effects. Now, this is again an heuristic picture. So for aficionados of, I want to see the details, let's go to the point. So how do you do time-dependent spin wave theory? Well, if you do Einstein permacompatible equilibrium, as you know, you have a fixed quantization axis that is, for instance, Z. And you can allow only small displacements around Z. These are your bosonic excitations, your collective excitation of the spin texture. But of course, if your collective magnetization starts to move around, there is no chance to define a good vacuum for that. So you have to go to a co-moving vacuum. This is, of course, very well known for people doing BCEs, a time-dependent Bogoliubov transformation. You need a moving vacuum. You need essentially time by time to define your annihilation and creation operators. So basically, we do an Einstein Permakov to low order, justified by the fact that the density of spin wave would be negligible, but we do it in a co-moving frame, capital X, Y, and Z. And this is if you want a time-dependent frame, you're jumping time by time on top of the collective order parameter. You have there your new vacuum, and these spin wave coordinates are in that frame. The fact that they change time by time, your annihilation and creation operators together with vacuum, will give you a self-consistent loop. The self-consistent loop translates in a mess. And I'm going, let's say, to try to guide you through the structure of the equation. So of course, if you look at them in this way, even if I tell you what are the terms, you're gonna get lost, but let's do it. So we have azimuthal and polar angle of your collective spin. This is theta and phi. And as you can imagine, of course, you are gonna have also your DR photonic amplitude. This is, let's say, not particularly shocking, are nonlinear equations. This is, if you throw away all the J dependence, this large N exact mean field solvability I was talking about. And now you're gonna have a feedback, right, from the spin waves, and they're gonna couple to the collective order parameter theta and phi via these kernels, small delta. Small delta is just a summation of several capital deltas that are quadratures of your Gaussian spin waves. And you get this, let's say, feedback because basically you need to solve the motion of the order parameter that will solve the motion of these guys that will feed into this equation, and you have to solve them forever and ever in a self-consistent loop. There is essentially a missing ingredient here. Is this epsilon is your spin wave density. You want to be sure that, let's say, inelastic scattering between spin waves is negligible, or better to say it happens very late in time, so that you can keep yourself with Gaussian theory of spin waves, and that's why you can solve essentially the problem for very large system size, 100, 200, you name it. That's not a problem. You're still solving a linear problem after all. All right, so I'm done. Quick advertisement. This business of time-dependent spin wave theory is not something we developed for this project. It's a long line of research that we started with Alessio Le Rose in Trieste back in 2017, and they're still continuing to give us satisfactions. That's a recent work still on dissipation, where we get also a little bit of dissipative limit cycles, but they are transient. With Sarofazio, the accent is completely on something else, is on dissipative state preparation. But please check, let's say, the version that you like more, quench, periodic drive, or dissipative state preparation if you want to see something different from time crystals. We have a little bit of time swap, so I wanted to advertise a nice poster by Shane Kelly, who essentially has found a new way to generate on-demand period doubling, period endoplets using nonlinear resonances in the phase space of long-range interacting magnet. He has a very nice analogy with the aliasing, that is these effects that you see, the blades of the helicopter like static, although they are moving very fast. I didn't know it's called like that in English. But the poster was yesterday, so talk to him. He is around, or just check out the paper. We are always happy to discuss and confront. Basically, I believe I'm done. This is my last slide. These are the 3 responses that are generally many-body in decay time crystals, and I'm open for questions.
Thank you, Jamil. At the moment, there are no questions, so let me ask a question. difficult for me. I'm not a quantum. Rosario and Odette. Odette first.
They saved you. You're muted, Odette.
Yeah, you have to unmute Odette.
Some organizers.
Was unmuted and now it's muted again. No.
Hello. Okay. Jamil, I am jumping to the rescue. We're going to anyway talk a bit more on Thursday. So thank you very much for the nice talk. I mean, there's an idea that I'm also going to pitch tomorrow in my talk, that at a certain point, your many-body system will develop due to its interactions or whatever it is that you are going to throw at it into a new normal mode. In this new normal mode, if you do ED on your system, right, your new normal mode will have a completely different eigenfrequency associated to it, and now you're going to apply time-dependent drives on it. Could it be that whatever it is that you write there is age, it just means that your new normal modes are now overlapping strongly with one another, and then they start to kick each other in a different way, that you're not just seeing a collective single mode that goes under period doubling bifurcation?
Yes, that's something that can happen there. I can kill the question in this way, or just tell you that, for instance, the fact that you don't just see the Dynamical crystal heating, but you can see other stuff was already in the experimental data or on the TWA slide by Andreas, where he was seeing that increasing the many-body interaction, it was seeing a dephasing from the period doubling. There can be a lot of stuff there, a lot of stuff. Simply the method can capture it. So, I mean, I have also, of course, ideas, right, to go there and to see what stuff is there. But sure, what you describe is completely possible.
Okay.
Yeah, Jamitra, I did not understand how is it possible. I don't know if I understood correctly or not, to have a crossover between the metastable time crystal and the decay time crystal. I mean, it should be a transition, because otherwise there will be metastability all the way down, or not.
Let's take a slide again. So you're worried about which part? The transition from here into the metastable time crystal.
Yeah. It's a transition, not a crossover. Did I understand correctly or not?
Okay, so if you are aficionado for the transition, this is what the spin wave density is showing you. It is jumping abruptly when you go from the DTC to the metastable time crystal. The question for me that would be for you, which is the order parameter? And I don't know the answer. So that's why I was cautious, and I was putting a dotted line. But I can accommodate both my, let's say, cautionary word, my cautious words, and your intuition. That's a jump, if you like it.
Thank you.
Can you connect what you computed to the work we heard in the morning from Andreas?
That's exactly what I was trying to say in my answer to Odette. That basically they have this last slide, right? When they increase, I think they call it EC, two-body collisions. That will be probably my J term if I got it right. And of course, it's very unreasonable and unlikely to think that if you change J a little bit, you're going to quick crossover into melting. You're going to crossover in no time crystal. You're probably going to crossover into irregular, probably. And actually, this is indeed what we see in TWA. So maybe if I have to make one last remark is, please, guys, really take this H as unknown regions, region where the method failed. There can be new, let's say, collective states at strong coupling, like Odette was saying. There can be just irregular dynamics. We simply don't know.
Okay. So thanks again, Jamir.
Thank you.
And we move on to the next talk, which is about is from Guido Hohmann, and it's about Higgs time crystal in a high TC superconductor. Can you?
Right. Yes.
Here we go.
Now you can hear me and see me, hopefully. Well, then I just share my slides. And all right. Can you see the first slide now?
Yes.
Okay, perfect. Okay, yeah, thanks. Thanks to the organizers, first of all, for having me at this very nice conference. And as announced, I'm going to talk about our proposal to make a time crystal out of a high-TC cuprate superconductor. And first of all, I would like to acknowledge my co-authors, Jason Kosmer and Ludwig Mattei, who made the work on this project a very enriching experience. So with this, I would like to move on to my actual talk. So first of all, I'm going to introduce the effective model that we use to describe light-driven dynamics in cuprate superconductors. And then I will show you the dynamical phase diagram that we have mapped out for driving the Z component of the electric field. And then I will focus on the discussion of the time crystal that we find in this dynamical phase diagram. And in fact, this time crystal appears for mono and bilayer cuprates. So let me just mention a few aspects of cuprate superconductors which are relevant for our model and for the mechanism that we propose. So here, the electrons form tightly bound Cooper pairs, primarily in the copper oxide planes. And characteristic excitations of these systems are Josephson plasma oscillations corresponding to Cooper pairs oscillating between the copper oxide layers. And these Josephson plasma oscillations are only observed in the superconducting phase, and they are linked to the breaking of U1 symmetry. So when the superconducting phase is entered, the order parameter takes a finite value and thereby spontaneously picks a phase. And generally, then there are two modes of exciting the order parameter. So first of all, there is the phase mode indicated in blue here, and then there's the amplitude or Higgs mode indicated by a red arrow. And while the phase mode is gapless for charged neutral system, in a superconductor, it acquires a gap because it couples to the electromagnetic gauge field. And therefore, in these systems, we have two collective modes which are both gapped. And as superconductors are approximately particle-hole symmetric at low temperatures, these two modes are linearly independent, but there is a cubic coupling term between the two modes in the Lagrangian that allows for Higgs excitations by two photon processes as sketched here. All right. So in our description of the light-driven dynamics in the cuprates, we focus on the interplay between the Cooper pair condensate and the electromagnetic field. And for this purpose, we have formulated an effective field theory whose static part is of the Ginzburg-Landau form. And then we added dynamical terms for the order parameter and for the gauge field. So to compute the time evolution of the order parameter and the vector potential, we discretize our theory on a three-dimensional lattice where the order parameter is on the bonds and the vector potential is where the order parameter is on the side and the vector potential is on the bonds. And alternatively, you can also see this as a three-dimensional lattice of Josephson junctions. And to account for the anisotropic structure of the cuprates, we also choose anisotropic lattice parameters. So in particular, the in-plane Josephson coupling is much larger than the interlayer Josephson coupling. And then we also include dissipation and thermal fluctuations in the equations of motions for both fields, and therefore, such that we can simulate the dynamics at finite temperature as well. All right. So once this whole model is set up, there are now different ways to drive the system. And for the remainder of this talk, I will restrict myself to the case where we add a driving term to the Z component of the electric field, which induces plasma oscillations along the Z-axis. And first, I'm going to discuss the results for a monolayer system, where the Z-axis parameters are uniform, so dn equals dn plus 1, and the same goes for the tunneling coefficients. And in the first step, we have then scanned the dynamics for different driving frequencies and different field strength. And in doing so, we obtained the dynamical phase diagram of this system. So here we found three phases. First of all, there's the normal phase. Then there's a heating regime where the condensate is entirely depleted. And most interestingly, there's this time crystalline regime that I will characterize in the following to point out how the dynamics here is distinct from the dynamics in the normal phase. So what happens in the normal phase? To see this, I would like to show you an example for one particular point in the dynamical phase diagram indicated by the cross. And as you can see, the amplitude of the order parameter oscillates with twice the driving frequency here, which can be expected due to this cubic coupling term in the Lagrangian. So here we have a superharmonic response of the order parameter. Now let's get to the time crystal. So first, you can note that this regime appears around the sum of the Higgs frequency and the Josephson plasma frequency. And okay, why doesn't it go to the next? Ah, no. Perfect. And once again, we pick one example here. Now we are at the bottom of the red time crystalline Tom. And as you can see here, the amplitude of the order parameter oscillates at a frequency that is notably smaller than the driving frequency. To be more specific, the amplitude of the order parameter oscillates at the Higgs frequency, so that in general, the subharmonic response is incommensurate with the drive. And as you can see, this behavior appears for a wide range of driving parameters. So it's not just the fine-tuned point in parameter space, and I will discuss its robustness against thermal fluctuations later in the context of the bilayer system. Okay. But first, let's elucidate a bit the mechanism behind this subharmonic response. So as I've shown you, normally the Higgs mode oscillates at twice the driving frequency, and the conventional resonance condition reads omega drive equals omega h over 2. And this resonance condition has been exploited in a couple of recent experiments to detect the Higgs mode. Interestingly, the time crystal that we propose is also a resonance phenomenon, and it originates from the same cubic coupling term in the Lagrangian. Here, the optical drive resonantly excites the Higgs mode and the Josephson plasma mode at the very same time. And this leads to this very distinct dynamics that I've already shown you, and which is further highlighted in the power spectra of the amplitude motion. So in case of the conventional Higgs resonance, there's only a single sharp peak at twice the driving frequency. And in contrast, for the time crystal, there are several sharp peaks below 2 omega drive, and the dominant one is at the Higgs frequency. Okay, now I would like to switch gears a bit and talk about bilayer group rates. So in order to capture this geometry in our model, we now introduce a staggered set of junctions along the z-axis. And therefore, there are now 2 chosen plasma modes in the system. The lower plasma mode corresponds to oscillating supercurrents along the weak junctions, while the strong chosen plasma, the upper plasma mode is associated with currents along the strong junctions. And the typical bilayer group rates, the Higgs frequency is in between the 2 plasma frequencies. All right. So the first question to ask is obviously, can we find the Higgs time crystal in such a bilayer system? And the answer is yes. We find it at the sum of the upper plasma frequency and the Higgs frequency. And before I discuss the results here, let me emphasize that now and in the following, we consider the numerical results for a large 3-dimensional system of about 10,000 sites and at finite temperature. So in this example presented on this slide, we have chosen a temperature of roughly 10% of Tc, and we chose a fixed driving strength and only vary the driving frequency and observe the dynamics for different choices of the driving frequency. And to spoil it already, the sum frequency of the upper plasma mode and the Higgs frequency in this case is 22.4 terahertz. And as you can see, the spectrum that we observe for the order parameter resembles the spectrum that I've shown you for the monolayer case before. So again, there is a very sharp dominant peak at the Higgs frequency, and there are a few other characteristic peaks below twice the driving frequency. And when we detune the frequency from the resonance condition, then the peak at the Higgs frequency becomes notably smaller and broader, and also the other characteristic peaks vanish. So unfortunately, the order parameter itself is not very easily accessible as an experimental observable. Is there a question already?
No.
Oh, 5 minutes. Okay, thank you for the sign. So therefore, we also looked at the dynamics of the supercurrents along the z-axis. And indeed, we also find a signature of the time crystal here, so which is the emergence of 2 side peaks at the driving frequency plus minus the Higgs frequency. And then in the following, we use the height of the blue detuned side peak to quantify the time crystalline fraction at various temperatures. And as you can see here in this plot, the temperature dependence of the time crystalline order is similar to conventional phase transition. And we find that the subharmonic motion is robust against thermal fluctuations up to roughly 20% of Tc. And let me mention again that here we are really considering a large system with long-range Coulomb interactions. So what happens microscopically in this large system? To show this, I would like to play a short movie in which you see the supercurrent field within the single BC plane And here we have used red arrows for the current along strong junctions and blue for the currents along weak junctions. And here I also show the integrated supercurrents in each row and also integrated along the third dimension. And for comparison, there's the drive, which in the normal phase is just in phase with the currents. All right. So let me start the movie.
Difficult.
So you see that despite the thermal fluctuations, there is a collective motion of the supercurrents, and the subharmonic response of the Higgs mode here manifests as a breathing motion when you compare it to the drive. So this is another nice insight into the many-body nature and the rigidity of this effect, I think. And exactly. And what we also did then was to check if this unusual dynamics could be observed in a pulsed experiment, because continuous wave lasers in this low terahertz regime with the strong intensities needed for the time crystal are not yet available, but potentially one could excite the some resonance in pulse fashion. And in fact, we found that also in the transient response here on the picosecond scale, that the supercurrents have this signature of the time crystal, which is the appearance of the two side peaks at omega drive plus minus omega h. All right, so I would like to briefly summarize what I've told you. So first of all, we have mapped out the dynamical phase diagram of cuprate superconductors for driving the C-axis electric field. And in doing so, we have identified a time crystalline state that is induced via some resonance of the Higgs mode and the Josephson plasma mode. And as I've shown you, this is a robust many-body effect that survives in the presence of thermal fluctuations. And with this, I would like to thank you for your attention, and I would be happy to answer your questions.
Thank you, Guido. Other questions? If not, I have a question. Your scattering is basically between the plasma waves that are made by Cooper pairs, right?
Yes.
And the Higgs mode, which is some sort of the strength of your, the density of your Cooper pairs, is it?
I would say both modes are fundamental excitation of the Cooper pair condensate, and you should maybe think of one of them more as this amplitude mode, and the other is kind of a phase mode coupled to the electromagnetic field.
Okay. And then it's a sort of Raman scattering between the two.
Yeah, I think these processes are reminiscent, so I think it's, yeah, one can see it in a Raman picture, yeah.
And if you have the time crystal, they must, one frequency must be commensurate with the other one to get it, or?
Well, that is not really...
The sum of the two is a third, and or is a multiple of the third.
Well,
all these peaks in between.
Well, as I've shown you, the motion of the amplitude is really different in this time crystalline regime compared to the normal phase, so where it always oscillates twice the driving frequency. So I would argue that this is a subharmonic response of the system.
I understand that, but aren't the frequency of these modes usually intrinsically determined by some material parameters, and they will be generically non-commensurate with each other?
Well, yeah, the material itself has a well-defined plasma frequency and a well-defined Higgs frequency.
Mm-hmm.
So what you need to do is, in order to create a time crystal, is to choose the driving frequency as the sum of the two, and this is
okay,
generally possible.
Okay, good. Are there further questions? If there are no further questions, thanks again, Guido. And we go to the final talk of the morning session. And this is by Gigius Slavlis. And he will talk about engineering time-space crystalline structures.
Okay, hello. Can you see me and hear me?
We can see you, we can hear you. And
that's great. And now I have to share the slides. Okay, can you see the slides?
Yeah, everything's all right. Go ahead.
Okay, thank you. So thanks for having me here. And today I'm going to talk about how to engineer time-space crystalline structures. So this talk is based on a recent paper that we wrote with Chuhui Fan, Egidius Anisimos, and Krzysztof Sacha. So first of all, I need to introduce the notion of a time-space crystalline structures. So these are systems that are periodic both in space and time. So the spatial periodicity arises from a periodic spatial potential. For example, it could be an optical lattice. And the temporal periodicity is engineered by choosing a proper resonant and periodic driving of this spatial lattice. So for example, if we have a one-dimensional periodic potential and we drive it in a suitable way, we effectively form a two-dimensional lattice, which we call a two-dimensional time-space crystalline structure. So in other words, in this case, when we drive a spatial dimension, we equip it with another temporal degree of freedom. Now, to make this construction explicit, let us take the example of a one-dimensional driven potential and see how this temporal structure arises. So first, let's say we have the classical case because it's good to build intuition, and also it is easier to determine the parameters from the classical case for the quantum case. So we start with a Hamiltonian of the system, which has a sine-squared potential that is driven side to side along the x-axis periodically with some cosine driving of amplitude lambda. Or in other words, so we can perform a canonical transformation to the oscillating frame of the lattice to separate the time-independent part and the periodic time perturbation part. Another trick that simplifies the analysis is moving to the action and angle variables. That is, action is defined in terms of a static Hamiltonian part, where its value is basically the area enclosed by the classical trajectory of a particle in the momentum and position phase space at a certain energy, and the angle is just the canonical conjugate coordinate of the action. So what we do here is just to rewrite the Hamiltonian in some convenient form. Now, the next step, what we do is we choose the driving frequency to be equal to the resonant frequency. That is, driving frequency is an integer multiple of the natural frequency of our system. So S determines at which resonance do we drive our system. And now what we can do is we can move to another reference frame, which is moving along a resonant orbit, and we get some Hamiltonian. We time average it, and we see that a crystalline structure appears in this reference frame. Now, why do we call this the temporal coordinate in a sense? Because if we take it, if we measure, well, if we fix a detector at one of the lattice sites, we will measure periodic detections of particles due to this periodic motion or a static lattice in the rotating frame. Now, it is important to stress that we have this structure at each of the spatial lattice sites. So effectively, we have a two-dimensional system. Now, to see that our approximation was valid, we can plot the solutions for both the initial Hamiltonian and the time average one in the action and angle phase spaces. So what we see on the left side is the solutions of the equations of motion for the first Hamiltonian, and we see that at the resonant action, some resonant islands form, where on average one particle spends a period in each island, a driving period in each island, and we see that the effective Hamiltonian effectively reproduces the same motion around the resonance region. So this is okay. Now, another point I need to mention is that in order to have the resonance structure that we need, we essentially need rather a deep lattice potential, which means that if we have a deep potential, our tunnelings can be at the ground state would be strongly suppressed. So we have to work near the top of our lattice potential. That means we have to consider as our basis the highly excited energy states of our system. So keeping this in mind, we can move on to the quantum case. So in the quantum case, well, we calculated to obtain the hopping parameters between the neighboring spatial lattice sites and between these temporal sites. To solve this problem, we essentially take the Floquet Hamiltonian, we time average it, and we obtain the eigenstate solutions of the time averaged Hamiltonian. And from all of these solutions, we pick the ones that correspond to the resonant energy of the system. So having these resonant states, we can construct a near state, a localized state, which will act as the basis of our time-space crystalline structure. Now here we have a picture of the solutions for the S=3 resonance case. So on the x-axis, we have 3 spatial sites, and each picture represents a time snapshot. So the first picture is taken at some initial time t0, the second picture at time equals half the period of a driving, and the third one is after the full period of a drive. So when we plot the Floquet eigenstate of this Hamiltonian, which is depicted by the black curve, we see that it respects the periodicity of the drive. That is, after one period, we get exactly the same densities. But now what happens to these localized wave packets? We see that they take 3 times as long to complete a full period. Now, here we only depicted a single one-year state per site, but in actuality, we have the number of these one-year packets per site is equal to the resonance number. So if we look at the evolution of these one-year wave packets at a single site, we would observe something like this. They just periodically oscillate back and forth. Okay, so having these one-year wave packets, we can use them to build an orthogonal basis for our time-space crystalline structure. That is, we can construct a tight binding model. So now here we have annihilation and creation operators in the second quantization form with some hopping parameters where the Latin indices indicate the spatial direction and the Greek indices indicate the temporal direction. So in the temporal direction, we have as many sites as the resonance that we consider. Also, it is possible to include interactions in this model, but they have to be sufficiently weak to not couple the resonance states with the other states of the system. So yeah, so this basically completes the effective description of our two-dimensional time-space crystalline structure, which appears due to the periodic driving of the one-dimensional system, but we can extend this to higher dimensions. So if we take a three-dimensional optical lattice and we assume that each spatial direction does not couple, our Hamiltonian of this lattice would be just a sum of the Hamiltonians of each independent direction. And of course, if we drive each of the direction properly, we in the end have a six-dimensional state, which consists of a product of each of the eigenstate of a Hamiltonian. Well, so we use these linear states to effectively build a six-dimensional tight binding model. Okay, so we have this high-dimensional system. What can we do more? Actually, we can engineer topological effects. So the main idea is that we can induce a tilt in the temporal direction to suppress the hoppings along the temporal direction, and then restore those hoppings with a two-photon process, which allows to imprint a flux along those a phase along those temporal lattice sides. So now we have an effective two-dimensional system and a flux piercing each of these system plaquettes. And what this allows to do is to create, for example, a ribbon which possesses this dispersion relation with topological edge modes. And if we plot the densities at a fixed momentum for a six-dimensional crystal, we actually see that, well, since we can't really plot efficiently a six-dimensional density, we take the standard on-site density definition and we trace it over the spatial parameters. And we see that at the edge of the time direction, we have this formation of edge states. So yeah, this is basically it. We can, well, combining time and space crystalline structures, it's possible to realize six time space, well, crystalline structures. The single particle and many-body condensed matter phenomena demonstrated already in time crystals can be also realized in six-dimensional time-space crystalline structures, and these structures can be endowed with synthetic gauge fields which allow to probe topological effects. And so thank you for your attention.
Thank you. The paper is open for discussion. I have a question concerning hopping in a space direction. If I have hopping in space, I can hop right and left. There's causality in time. I can only hop forward. I didn't succeed so far in hopping backward. Does that make a difference?
I mean, okay, so essentially we have an effective structure of three wave packets oscillating back and forth on that single lattice side. And this structure, well, when these wave packets overlap, the particles can hop from one to the other. So this is the temporal direction hoppings actually. So it's not like a hopping in time forward and back.
Okay, can you elaborate how that? Then what is hopping in time?
Hopping in time would probably be these overlaps that we see. Well, we have these wave packets that overlap and moving around, but when we time average it, we have some overlaps among these wave packets, which essentially give us this hopping along the time direction. Well, temporal direction. It's not really time, but effectively it's described, well, it appears due to this resonance driving.
Okay. Are there further questions? If not, let's thank all the speakers of this morning, and I hand over to Rosaria.
Okay, so just to say that, so first of all, thank you, Thomas, for chairing the session. And so we start this afternoon at 2:30. So just now it's lunch break, or depending on the time zone, and see you in roughly 2 hours. Okay, see you.
See you.
Hello, Rosario.
Hi, good.
I am at the place. Okay.
So I think it's good. There was something I wanted to ask you, but then now I forgot.
You forgot.
I forgot. Yeah, sorry.
There is still some time, you know.
Yeah. So if I. So at the end, yeah. So the poster session worked out fine yesterday. I mean, this was my first experience of this kind. The only bad thing is that those people that have the poster, they cannot move around. This is the only limitation. I don't know how if this can be solved.
Actually, this poster, first of all, the number of posters was not that big. It was good because you know. And I was recently I attended poster session where there were breakout rooms, and inside breakout rooms there are another breakout rooms. Total mess. Total mess. You know, when you enter, you know, the last breakout room, nobody can enter, you know, as a second person. It was disaster. But in this way, no problem. It was very, very, very efficient. Yeah.
So let's see. Probably we can. Walter, to say.
Okay, we should. I will.
Probably you can admit people, right? So.
Yes, I will admit Kuba Zakrzewski.
Ciao, Marco.
Okay, Kuba.
So I think Marco Schiro is.
Yes. I try to unmute him and to unmute this.
I unmuted myself. Hello, Rosario.
Hi.
Hello.
Hello, everyone.
Ciao, Marco.
Hello.
Hello. Okay. I tried to call you, Krzysiek, but host is not letting me in, but you didn't reply to the phone.
Okay. Okay, we are neighbors, so that is, you can even shout.
Yeah, well, normally I don't have to shout. It's enough that I speak normally, and Krzysiek knows everything what I am saying. These are new walls.
Marco, did you check the presentation?
Yeah, I did a check, so it should be fine.
Okay.
Whenever.
Kuba, you should remember that it is recorded and live streaming. So that is.
It's recorded, so I shouldn't say my usual words, right?
Sorry for interrupt you. Can we make a test briefly with Professor Lezanowski? Thank you.
Sure.
Jawohl.
Hello.
Hi, good morning.
Hello.
Oh, good afternoon.
Hello.
Let me just share the screen, okay? And then we see whether this works. Just a sec. I go large here. Okay. Right, do you see my screen?
Yes.
Yes.
Do you have audios or videos in your presentation?
No videos.
So perfect. We are done.
Do you see the pointer?
Yes.
Perfect. Okay, so then we are good. Okay.
Thank you very much.
All right. Thanks a lot. See you later then. Yeah.
Yes.
Yep.
Thank you. Sarah, excuse me. I'm still meeting Professor Taheri.
Okay.
Okay, Walter, I would like to ask you to make Jakub Zakrzewski a co-host, because then he can mute and unmute himself. Okay.
Yes. Where is he, in the waiting room?
No, he's in the meeting. Is Jakub it's with a Z. I'll pronounce in Italian.
Okay.
Zakrzewski.
Okay.
Perché farà, he will be the chairman.
Thank you.
Done.
Thank you.
Thank you.
And the second speaker is Hossein Taheri, and this guy is from US, and probably he will join us just before his talk. So that hopefully everything will work.
Hopefully he will wake up.
Yeah, this is the other point.
It's relatively early, right?
So is the what, 8 o'clock or 7 o'clock for him?
May I make the test also with Professor Das, since he's in?
Sure.
Professor Das, can you hear me?
So don't worry, Walter. If
he's unmuting.
Okay.
Hello, sir.
Hello. Excuse me. Can we make the test? Can you please share your screen?
Okay. One second.
Do you have any audio or video in your presentation?
Yeah, I have.
Okay, this is important to check. No, alternativo. Okay. We can see your screen. Okay.
You can see it?
Yes. But I can't hear you very well. You are using earphones with mic, or you're using the microphone of your computer?
Sir, I'm using the microphone. Can you hear me?
Yeah, now it's okay, I think. On my computer, I mean, I hear well.
Okay.
Just talk a bit louder. Thank you. Okay, let us check the audio and the video. You have?
Probably. So did you have a video in your presentation?
No, sir. There is no video.
There is no video. Sorry, there was.
No.
Okay, so we are done. Thank you.
Okay. I am.
Thank you. So may I ask Professor Fernando Iannini to? Okay, here we are. Let me unmute you. If we can make the same test, please share your screen.
Okay. Now, can you hear me now?
Ooh.
Yes.
Hi.
Very well.
Your microphone is quite sensitive.
So how do I share my presentation? My slides presentation is just.
You should. Are you using PowerPoint, Keynote?
Just a PDF.
PDF. Okay. Open your PDF. Then go to the Zoom menu bar on the green button. Share screen.
Okay.
And then you will see you have several options. You have to choose the software you are using to show the PDF. Okay.
Okay. I chose the PDF that I'm open here. Can you see my presentation?
Yes.
Okay.
You can see it. You don't have any audio or video in your.
No. It's just this PDF. Yes.
Is it possible? This is not the slideshow mode.
No.
Right?
No. Let me just. Let me see if I can put in the slideshow. Maybe it's this one here. Okay.
Okay. Fantastic.
So, can you also see my mouse and my pointer? That just work as a point. Okay, so that's great then.
Yes.
Okay.
Perfect. Thank you very much.
Okay. Thank you very much.
Okay.
So Fernando, you can stop sharing so that we.
Yeah, I'm trying to close my PDF here.
Okay.
Just a second.
So, Professor Cabot, can you hear me?
Yes, I can hear you.
Hello. Sorry. Can we try, please, your screen sharing?
Yes.
Okay, bye-bye, everybody.
Okay. Can you see it?
Yes. Can you launch the slideshow mode? Okay. Perfect. Do you have any video or audio in this presentation?
No, I haven't. Just a
Okay,
slide.
so we are done. Thank you very much.
Thank you.
From our side, except for Professor Taheri, we made all the tests, Saro and Christoph.
Yeah, for
Oh,
him it is 5. If it is 5:26, so I think he's still sleeping.
Yeah, I think.
I mean,
it's okay.
who gave him the talk at 6 a.m.? It must be Krzysiek Sacha because he gets up at 6. But I would not accept the talk at 6 a.m.
So Walter, I think we can admit people, everybody. I mean,
okay.
We are close to start.
Let me do it. Done.
Good. So we have still nearly 3 minutes. Maybe let's wait 1 minute more.
Oh, it's better to wait because people appear at the time and then they come in the middle of the ceremony, especially in the morning. Okay, I think that that the number 38 has stabilized. So I think we can start the session.
Share my screen.
Yes, Marco Shiro from Collège de France will give
you see my screen?
And before Marco starts, I congratulate you on ERC.
Thank you.
Consolidated, which I just found on the web. Okay, so Marco will tell us about quantum melting of a dissipative time crystal.
Okay, thank you very much for the introduction. Thanks for the invitation. I'm enjoying a lot this online conference. As someone said, being interested this week would have been great, but it's great to see that things are still happening. So the topic of my talk today will be about dissipative time crystals. We heard quite a lot this morning, so I will try to connect to those presentations. Let me first of all mention the main responsible for this work and my collaborators. So this work was done mainly by Orazio Scarlatella, who is a postdoc at Collège de France. And we enjoy collaboration with Ash Clerk in Chicago and Saro Fazio at ICTP. So this is my outline. I will give you a bit of introduction time crystals in open quantum system. As I said, most of this part has been covered. And then I will get to the core of my presentation. I will present a model for dissipative quantum time crystal built out of van der Pol oscillators. I will first talk about the classical case and then move to the quantum domain. And I will discuss a specific limit of this array of van der Pol oscillator, the so-called large connectivity limit, in which I will discuss how this dissipative time crystal grows out of a normal phase and how it is eventually destroyed or not due to finite quantum fluctuation. Okay, so the starting point, I think we are, as we've seen this morning, we are going toward a classification of time crystalline phases of matter, and we have heard and I would say we understand quite a lot about Floquet time crystals or discrete time crystals, which are protected by many body localization. There have been various theory works and experimental demonstration. So from this point of view, one usual attitude is to think that dissipation usually is detrimental for this kind of Floquet time crystals because MBL is usually destroyed by dissipation. And an interesting question that has been asked by many people is, can we have genuinely dissipative time crystals which are not destroyed or actually need dissipation to exist? And we have heard many already few talks addressing this point. In particular, Anna Sampera gave a beautiful presentation this morning that essentially covered a good deal of my introduction. So thanks to her. And also we heard about experiments on the decay model and theory in the decay model. And Fernando will talk about boundary time crystals. So we have, there are several angles to which you can address this question. So let me first step back and think about dynamical instability in classical systems. And I think tomorrow there will be a talk on that, which I'm looking forward to hear. But of course, if you remind yourself of dynamical systems, you know that there is a rich behavior emerging out of nonlinearities, noise, and dissipation, and a variety of instabilities that happen at finite momentum, at finite frequency. You can have period doubling, you can have limit cycles, you can have various sorts of flow. And so it seems natural to think that the realm of dissipative system is a good starting point for to look for this kind of phase transition in the time domain, if you want. So in this talk, I will take this motivation and I'll try to move toward the quantum domain. So I will work in the framework of open quantum many-body systems. So I will go very quickly on this because we have had this morning an introduction. I will work in context of Lindblad master equation. So the system is described by a density matrix and its evolution is described by an equation that contains a competition between coherent dynamics and dissipative jumps. You can think of it as arising from tracing out the degrees of freedom of the environment and under the Bohr-Markov approximation, but there are various ways you can get to this Lindblad evolution. And this dissipative part that is you see here on the right contains the so-called jump operators, which describe the effect of the environment on the system. And so this is enjoys some nice properties, a linear, completely positive, trace-preserving quantum map that takes a density matrix and gives you back a density matrix. And it's a linear evolution, which is important and allows, for example, in a good variety of cases, to diagonalize the Lindbladian and look at the spectrum, the right and left eigenvectors. Since, as we know, the Lindbladian is a non-Hermitian operator, and you can use this basis to decompose the evolution of a density matrix, which from which you, given an initial condition, you have a superposition of decaying modes with which have eigenvalues with a negative real part, which correspond to decay, and zero mode, which correspond to a stationary state. And under rather general hypothesis, if you don't have specific symmetries, if you are don't have decoherence free subspaces and so on. The stationary state is unique for finite system, is analytic, and so the question one could ask is what happened to this spectrum of the Lindbladian as the limit of thermodynamic limit is taken. Let me comment right away in terms of, from this perspective, how time translational symmetry breaking would appear. I didn't say it, but this Lindblad operator I'm having in mind is completely time independent. So enjoys continuous time translational symmetry if you want. And so in this context, a spontaneous symmetry of time translational symmetry would appear as a vanishing of Lindblad real part of the Lindblad gap and a finite imaginary part. So I think Fernando Iemini will discuss this more in detail in the context of stock on boundary time crystals. For what concerns my presentation, I will address these spectral properties of Lindblad problems from the length and the point of view of Green's function, spectral function of Markovian system, and the reason is that, as I will try to convince you, those objects play a rather important role for the understanding of how dissipative time crystals emerge, and they are also directly measurable experimentally. So let me just give you an example. There are a variety of Green's functions. We will focus mostly on the spectral function, or the imaginary part of the retarded Green's function, which is a sort of density of state. And we know well in equilibrium what kind of expression this density, many-body density of state, single particle density of state has. It's a sum over eigenstates. You have delta function that are located at the transition between many-body eigenstates with matrix elements which are given by the operator. In this case, is a creation annihilation operator that connects two eigenstates. And so one can generalize this so-called lemma representation, this very general representation of spectral function for Markovian system. And we will use that. And the bottom line is that you have now, you don't have any more delta peaks, which are broadened by the fact that the system has finite lifetime. But otherwise, you have a general structure and analytic properties which are rather similar. And as I said, those objects are not that exotic in the end. They can be measured through transmission, for example, if you have circuit QED architecture in mind. If you are more in quantum optics, from the quantum optic community, this is just one example of the famous Mollo triplet. So those objects are also rather easily accessible. So let me, with this introduction, get into the somehow the main part of my talk. I would like to discuss this dissipative time crystal in arrays of quantum van der Pol oscillator. So I thought I should introduce the van der Pol oscillator, which is incredibly simple but rich example of nonlinear oscillator. The story is also quite interesting. I don't know if you know it, but I found it amusing. This equation was written by two electrical engineers working at Philips in the late 20s. And they were playing with electrical circuits and vacuum tubes. And they wrote this paper that they call frequency demultiplication, in which they say, we found out that once you drive this circuit, you can have a response which rise at frequencies which are submultiples of the frequency of the applied. So this is, if you like, already a signature of subharmonic response in this context. The even more amazing thing of this work is that those guys were, to probe their system, they were coupling this circuit to a telephone. Okay, so, and they were converting this electrical signal into sound. And so they write this comment at the end of their Nature paper that says, often an irregular noise is heard in the telephone receivers before the frequency jumps to the next lower value. However, this is a subsidiary phenomenon, the main effect being the regular frequency demultiplication. Turns out that this noise is a demonstration of chaos that they kind of discovered 30, 40 years before before Lorentz and others even wrote down a strange attractor. So this is just to say that this van der Pol has a kind of a rich story, and I also added here let's say modern day van der Pol oscillator. There is a very nice article on the New York Times that I encourage you to read if you are interested. This kind of equation is, as I said, the simplest probably nonlinear oscillator, described in a nutshell a system developing self-sustained oscillation. And how do you see that? Well, you see this equation as the first, let's say, two terms look like a regular harmonic oscillator, and then you have a nonlinear damping. In this nonlinear damping, you see that depending on the value of x of your variable, when x is very small, when x is very large, acts as damping and brings it down. When x is very small, it changes sign, acts as a negative damping, which leads to amplification. So this is a sort of feedback that gives you oscillatory, self-sustained oscillation. The form of this oscillation can be very rich. It doesn't need to be a simple sinusoidal form, and depends on various parameters. And this has been studied in various domains, from electrical engineering up to biology. What I want to somehow highlight here is that in the small amplitude limit, this equation, which is a second order differential equation, reduces to a linear first order equation. And this is what I like you to keep in mind, because now I would like to try to quantize this or present a model of coupled quantum van der Pol oscillator, and try to convince you that in a certain limit you recover exactly that. So in order to do that, I will write down and study a Lindblad master equation, as I introduced before, which describe array, a lattice of bosons, which are described by this creation annihilation operator A on each lattice site. Those bosons are nonlinear oscillators. So you see they have a frequency omega naught and some self interaction. You can call it Kerr interaction. And they are subject to, on each side of this array, they're subject to dissipative processes, which are local. And we will consider two processes, which kind of are the main ingredient here. One body pump, which inject bosons into each lattice site, and two body nonlinear losses, which are described by those two jump operators. Just let me emphasize that I'm using units in such a way that essentially the strength of the dissipation, the losses, it's eta, and the pump is just R times eta. So I will study this model mainly as a function of R, which is the ratio between pump and losses. So this master equation enjoys some symmetries. First of all, the problem is time independent, so there is a continuous time translational symmetry. And there is a U1 symmetry associated to the fact that I can make a phase transformation and a jump operator, and the density matrix, the master equation remains invariant. The Hamiltonian is invariant, and the jump operators, the combination of L and Dagger is also invariant. This model is not that, it's not only a theoretical exercise, is actually something that can be realized in experiments with circuit QED arrays and with ultra cold atoms. We have heard this morning from the talk of Masaito Ueda that inelastic processes can give rise to two-body losses in cold atoms. And even in circuit QED, there is a way to engineer these correlated dissipative processes. Okay, so with this setup, let me first of all show you that what I said before is true. In a certain limit, let me show you that we will recover the classical arrays of van der Pol oscillator, and then we will move ahead from there. So this is the limit of the so-called semi-classical limit, in which all those bosons are, you assume they are in a coherent state. And so in equilibrium state, you can write down their equation of motion, and the equation of motion for those bosons, if you somehow disregard completely the noise, reduces exactly to the small amplitude limit of coupled van der Pol oscillator. So you have dynamics for this oscillator on each side. You have a nonlinear oscillation that are due to the Kerr nonlinearity. You have this nonlinear damping that I mentioned before, where you have, again, as a function of a damping that depends on the amplitude of the local bosonic field, and then you have a linear coupling between different bosons. Now, if you study this equation in the uniform limit, you realize that, as we were saying, a textbook example of limit cycle, you have an oscillating solution that emerge. This oscillating solution emerge for any value of the pump to loss ratio. So as soon as you start driving, the system enters into this oscillatory regime. The frequency is set by a combination of different parameters, including the bare frequency, the hopping, and the interaction strength. And the amplitude of this bosonic field is set by the drive. So if you, so the starting point is that we have an array of classical van der Pol oscillator. If you introduce a little bit of noise due to the residual quantum fluctuation, if you think that they are small, you can, not surprisingly, convince yourself that this model, this system can desynchronize, if you allow me to use this term of synchronization and limit cycle in the same context. And this was discussed, for example, in this paper by Lee and co-workers. But of course, this regime of small quantum fluctuation starting from the semi-classic is one angle. I would like to present the result from a rather opposite regime, in which we study this array when we have only few bosons per site. So the semi-classical approximation is not really a good starting point. And so to do that, we have developed an approach that I think is very promising for open quantum system, that relies on the idea of taking the large connectivity limit of a Lindblad master equation. So this is a little bit the sketch. I will enter more in detail of what that means, but on the left side, you see this array where you have a local Hamiltonian, local jump operators, and hopping between the different degrees of freedom. And then you can study this problem in the limit in which the connectivity of the lattice, Z, the number of neighbors, goes to infinity or becomes very large. And in those two limits, you reduce the problem to something that is obviously much simpler, but quite rich, as I will try to convince you. In one case, that is the exact infinite connectivity limit, this corresponds to what is called Woods-Wheeler mean field theory, and the picture is that your entire lattice maps into a single site coupled to a self-consistent field. And in the limit of large but finite connectivity, this will correspond to what is called dynamical mean field theory. And in addition to this coherent field, you will have a non-Markovian bath, which mimic the effect of the rest of the lattice. Okay, so this approach, you can think of it as a sort of quantum mean field limit, in the sense that retains the discrete nature of the problem. It's a single site coupled eventually to either to a field or to a quantum bath. So there are more details on this approach that is rather general and goes beyond the van der Pol problem in this paper. Let me discuss the results and in the context of this dissipative time crystal. And I will first analyze the infinite connectivity limit, that, if you like, is more simple, but quite interesting. So this infinite connectivity limit, as I said, corresponds to a completely factorized ansatz on the density matrix. This corresponds to Woods-Wheeler mean field theory. So you are reducing your problem to a single quantum van der Pol oscillator coupled to self-consistent field. And what I'm plotting here is the phase diagram as a function of pump to loss ratio and hopping versus interaction ratio. And you see there is a critical line that separates what we call a normal phase, in which the system goes to a stationary state, from an oscillating phase, in which the system develops a many-body limit cycle. Now, let me emphasize that, just to compare, in the semi-classical approach that I started with, the entire region of R greater than 0 would be completely oscillating. Okay, so we see already that treating, including quantum fluctuation in the regime of few boson per site change quite dramatically the picture and introduce a large region in which the system remains normal. And I will discuss exactly why is that and how this comes about. So the two main issues that you think that you have to, that I would like to highlight is that there is a critical transition, a critical point as a function of the hopping, and also there is a threshold drive. You don't probably see it because this scale is not particularly well chosen, but this line, this horizontal line is around R equal 1, meaning that you need a threshold drive in order to enter to this oscillating phase, and I will explain exactly why is that. So this approach suggests us to look a little bit more into the details of physics of the quantum van der Pol oscillator, which is a problem that is attracting a lot of interest in the context of synchronization, mostly for coherently driven oscillator. We will not consider this case. We'll consider the case in which, as I said, there is no coherent drive, but only incoherent pump and two-body losses. This model is nevertheless quite interesting. It turns out that the steady-state density matrix for this nonlinear quantum oscillator is known analytically. This is a work by Mark Dickman that goes back to the late 70s. And it's known that this boson go into an incoherent mixture. So the density matrix is diagonal in Fock space. There is no coherence, of course. And the stationary state density matrix is completely independent from the interaction. It only depends on the ratio between pump and losses, this parameter R. And as a function of R, as a function of the ratio between pump and losses, you already see an interesting effect. The density matrix, the probabilities of having n boson per site, develops what is called a population inversion. You see that a small drive, this quantity is a decreasing function of n. A large drive, instead, you have you have a non-monotonicity, which means that higher occupancy is more probable than lower occupancy. We realize that there is more to this if we actually go beyond the steady state properties and we look at the green function of this problem, and I will show you why this is relevant for our problem. But if we look at the spectral function, so the density of state of the quantum van der Pol oscillator, we found a rather surprising result. At weak drive on the left side of this plot, you'll see a series of peaks which are broadened by the dissipation. This is not so surprising. When you don't have interaction, this is essentially Lorentzian. When you have interaction, you have more peaks. However, when you increase the drive above a certain threshold, you see something that at first puzzled us quite a lot. You see that the density of state at positive frequency becomes negative. So you see there is an entire range of frequency at which the spectral function of those bosons becomes negative and vanishes at a certain frequency. So what is the physical meaning of that? The spectral function contains essentially measure the power that the system absorbs from a perturbation from a weak coherent driver frequency omega. Okay, so typically you would expect this quantity to be positive, but when this quantity is negative, it means that the system wants to develop gain, wants to actually gain energy from the external perturbation. So this is an incipient effect that leads eventually to energy emission. And let me guide you through this kind of interpretation of this dissipative time crystal as a sort of energy emission. So how do you understand how a dissipative...
Five more minutes.
Yes, okay. How do you understand if a dissipative time crystal emerge? What you do, you have a single site problem. What you have to do, you have to put a small symmetry breaking field and look for a self-consistent solution. And you see that by perturbing with an oscillating field, you obtain first the order parameter is set by the retarded Green's function, that is the susceptibility to the breaking field. And then you have a self-consistent condition, and you obtain this equation. The self-consistent equation tells you essentially the location of the boundary between normal and dissipative time crystal. And from this equation, you immediately see that in a generic condition, you would expect this retarded Green's function to have a finite imaginary part. And so you are not able to solve and satisfy this equation unless the system develops a negative density of state and develops gain, in which case you have a frequency at which the system is essentially dissipationless. And when the system is dissipationless, it can emit and oscillate at a certain frequency. Let me skip this in the advantage of time. I want to conclude by saying what happened to this picture when we include finite connectivity. And so this is done by what I call dynamical mean field theory, in which you have now to solve a single side which is coupled to a coherent field and to a non-Markovian quantum bath. This is a problem which is much more challenging than the previous one. Nevertheless, we developed an approach that is powerful and non-perturbative approach in which we expand self-consistently in this non-Markovian bath. I will not enter into the details, but if someone is interested, I'll be happy to discuss. And this is somehow the main result of this approach. Is the same phase diagram as before, but now as a function of lattice connectivity. So the gray line is the infinite connectivity mean field limit, Gutzwiller mean field limit. And as you decrease the connectivity, you increase the quantum fluctuation from the neighboring sides. And you see two main things that are somehow the main result. First of all, the dissipative time crystal remains. And there is still a region, a high drive, in which the system develops oscillation. Nevertheless, the effect of fluctuation is to shrink, to melt this dissipative time crystal. And maybe the last thing that I want to say before closing is that the mechanism through which this happens is a genuine non-equilibrium mechanism for the destruction of an order phase. And let me argue where this comes from. Again, you can add a small symmetry breaking field, and now you realize that dynamical mean field theory gives you two contributions to this symmetry breaking field, one coming from the coherent field and the other coming from the self-consistent bath that describes the finite number of neighbors. And now this self-consistent bath enters in this equation here, and you see that the boundary between the DMFT boundary with respect to the mean field one is substantially pushed toward higher values. And this is due to the fact that the bath is able to destroy the negative density of state through a mechanism that we call hopping-induced desynchronization. That is somehow physically you can interpret as the bath absorbing the energy that the system was taking from the perturbation. With this, we check that this effect does not come from noise. And you might have think that the effective temperature here is increasing, but as we see as a function of connectivity, this remains rather stable and weakly dependent from the connectivity, while the phase diagram change quite dramatically. Okay, with this, maybe I should conclude because I see the chair getting ready. So my conclusion, I hope I give you an overview of the dissipative time crystal classical versus quantum. The message for what concerns this array of Van der Pol is that quantum fluctuation partially melt, but do not destroy completely this dissipative time crystal phase, even at finite connectivity. And nevertheless, the mechanism for this dissipative destruction of an order phase, I think it's very interesting, and we would like to look more and use more this new technique that we developed. And with this, I would like to thank you for your attention.
Thank you, Marco. We have, well, 1 minute for one short question. So Jamir Marino was first. So please turn off his mic. Turn on his mic.
Hi, Marco. So rather than being a question, it's a comment. I'm going to make a comment, and I want to know if you commit to the statement or not. After all, because you need to generate synchronization always a damping. You need always a dissipative dynamics. Having quantum synchronization means basically always having at most a semi-classical synchronization, a leading classicalizing with few quantum correlation effect. If you want, I am just rephrasing the usual old question, what is quantum in dissipative phase transition? And the answer is can be quantum only in a certain crossover in time. But asymptotically, and here you need to go asymptotically, will be always leading a classical behavior, whatever operation you try to do. Would you commit with that or not?
No, I think the message of this talk is rather the opposite. This talk shows you that quantum synchronization is much more similar to, if you like, non-equilibrium superfluidity than just the classical van der Pol. You need to have gain, and first you have gain, and then you develop, if you want, phase coherence between the oscillator. And this is a mechanism that you don't have in classical synchronization. That's simple. And then, for what concerns time scale, I'm not sure, because this is a completely dissipative problem. This is a stationary state, so there is no. I mean, this is there is a bath, so it's a truly stationary state. Then one might wonder whether it would decay. But I would say the main message of this is that really both the synchronized phase, how does it develop, and how it is reduced is something that I don't think has analog with noise or effective temperature, but it's really a matter of, it's a very, really a dynamical instability, like you have in lasing or like you have in superfluid accident polarity.
Okay, I guess we have to stop at this moment. Thank you, Marco, very much. And welcome Hossein Taheri, who woke up, as I see. So please, Hossein, share your screen with us, if possible. And you are unmuted, and the floor is yours.
Thank you. So can you see my screen?
Yes, we can see your screen.
And hear me well?
Very well.
Okay, great. So thank you very much, the organizing team, for inviting me to this interesting conference. It's a pleasure to be among a distinguished list of speakers. I am Hossein Taheri from the University of California at Riverside. I'm a research faculty here. I'll be presenting some results based on our recent research on time crystallinity in kernel-in optical resonators, and particularly about dissipative discrete time crystals. So I'm going to start with a quick outline of my talk. Before that, I'll make sure that I move my own screen to the corner in case that blocks for anyone. So I'll start with a very brief introduction to time crystals, because I believe it's been covered very well from different angles in other talks. And then I will present a quick primer on optical frequency combs, KER microcombs, which are the platform we are using for our demonstration. And then I will proceed to our results. So first, starting with a brief introduction to time crystals, know that time crystals were introduced as the temporal equivalent of solid-state spatial crystals. The idea was introduced in 2012 by Frank Wilczek and can be considered an extension or lie in line quite well with the temporal evolution of the concept of time from Newton to Einstein. Know that Newton believed in absolute time, but Einstein showed that actually it's relative. It should be treated on the same footing as time, as space, and combine them into space-time. So the concept of time crystal fits in well here. It's also intimately related to the concept of symmetry breaking, which was suggested by Lev Landau as a reliable criteria for classifying the different phases of matter. So this concept is now being studied as a new state of matter. And originally, of course, the idea focused on equilibrium systems, but it was shown that that proposal does not work. So researchers proceeded to non-equilibrium systems, particularly periodically driven systems. So we're not going to look at continuous time symmetry breaking, but in fact, discrete time translation and its breaking. So that happens when we have a drive with periodicity, say t, and the response of the system, the behavior of an observable in our system, has a larger integer multiple periodicity, in this case shown here with 2t. And when we have that, then we proceed to, we get a discrete time crystal at DTC. We can define a size as the ratio of the response to the drive time. And then in experiments particularly, we look for some signatures. One of them is period multiplication or subharmonic generation. And other properties are also required, for instance, long-range order in the temporal sense, and also many-body interactions in the sense that the period multiplication which we observe should be a result of many-body interactions. Now, of course, there have been a good number of demonstrations so far. I want quickly reviewing the first two demonstrations. One of them was in a one-dimensional array of trapped ions. The other one was in a 3 dB ensemble of NC defects and NB defects in diamond. And when the magnetization properties of these two systems were measured and analyzed, characteristic subharmonic generation was observed. Now, these demonstrations have been mainly focused on isolated or closed systems in which the coupling between the system and an external path or the environment is vanishingly small. And these systems are, of course, very interesting, particularly because of the curious ways that these systems find to avoid or postpone thermalization or heat death. But for practical applications, it's inevitable to consider systems in which we have dissipation and heat, particularly for real-world applications. And these systems, the heat which is generated as a result of dissipation can destroy the crystalline order. So there should be an environment, and there should be non-vanishing coupling to the environment to channel out generated energy. And that gives rise to the concept of a dissipative discrete time crystal. And that is what I am going to demonstrate in our system. So that was my quick introduction to time crystals. Now let's go to Kerr microcombs. Everything starts with Kerr nonlinearity here, so let's talk about that. It's the dominant nonlinearity in centrosymmetric materials. The susceptibility is chi3, or the cubic nonlinearity. For a single mode field, we can simply write the Hamiltonian as the sum of the Hamiltonian of the radiation and the interaction Hamiltonian. The coupling coefficient G in this Hamiltonian is proportional to the chi3 susceptibility or with the N2 nonlinearity. And what happens in a bulk medium is that we have two photons of pump which are annihilated, and instead they generate two photons, the signal and idler frequency, one of them with larger frequency and the other with smaller frequency. But the point is that in a system, especially in bulk medium, the efficiency of the process is not so high as to give rise to a lot of sidebands. So we study this process not in bulk medium, but in a microresonator, a high quality factor microresonator. And what happens is a degenerate forward mixing cascaded by non-degenerate forward mixing process, and then the cascading of these two effects, in which we have the pump and the two photon pumps generating sidebands, and then those sidebands performing for mixing with the pump itself and also with each other, and then the cascading of the effect leads to more sidebands. The threshold of this process is, of course, inversely proportional to the nonlinearity coefficient, but also inversely proportional with the quality factor of the cavity, which is a measure of the amount of energy stored in the resonator over the amount of energy which is dissipated or lost in every cycle of the radiation of that particular radiation of light. And of course, it's also proportional with the volume, the mode volume of the field in that resonator. Now, these resonators have been fabricated in various shapes. In spherical, that was the starting point, I believe, with Serge Haroche, and then other types of microresonators then moved from even cylindrical and toroidal in crystalline to integrated materials. And different types of materials, for instance, calcium fluoride, magnesium fluoride are the crystalline types, and silicon nitride and silicon dioxide are two examples of integrated resonators that are commonly used in this platform. And the quality factors we can get in crystalline resonators, something usually between 10 to 8 to 10 to 11, and in integrated resonators, something between 1 million to 100 million, usually in the lower 100 million. So I think 10 to 7 is a better number these days. The platform we have used in our experiments is the crystalline magnesium fluoride resonator. Now, when we have this schematic microresonator, we drive it with a CW continuous wave laser pump. It generates a frequency cone, an array of frequencies. So let me show you another schematic here. And because it looks like a cone, we call it a frequency cone. Now, when you look at the frequency, the spacing between adjacent harmonics is the repetition rate, or almost equal to the free spectral range, the FSR of the resonator at the position of the pump. And if the system and the generated frequency column is self-synchronized, phase locking occurs, and this frequency picture corresponds to a very short pulse. And this is what we call essentially mode-locked pulse, which is also generated in a mode-locked laser, but the mechanism of generation is, of course, different. Now, these structures can be used as rulers of light, especially because after synchronization, after generation of a stable pulse, the frequencies separating these harmonics are very, very exactly the same. And the repetition rate, the amount of time separating two consecutive peaks of the pulse train in the pulse train are also very accurately the same. So we can use them for many for very precise measurements, and that's why the 2005 Nobel Prize went to partially, of course, half of it went to frequency cones. Now, a quick point I want to mention here: synchronization process that occurs in these structures cannot simply be reduced to a phase model and is different from the Chromoto model, even though it was suggested as though back in 2016. Now, to experimental demonstrations, when we have normal dispersion, this is the type of spectrum we get. We get a bright soliton with the characteristic hyperbolic secant envelope of the spectrum. And that gives rise to a pulse, to a soliton, which is called a dissipative Kerr soliton in our literature. And that results from a balance between dispersion and nonlinearity. Generally, a soliton in a system, in any nonlinear system, arises from the balance of nonlinearity and dispersion, and a very excellent, I believe, description of how that happens appears in Butcher and Cutter. And in the case of a dissipative system, there is also another balance of gain and loss, and we have shown how that gives rise to even dark solitons in the normal dispersion regime. Okay. Now, quick point about the mathematical description. I showed the Hamiltonian for a single mode field. Let's go to a multi-mode field. We can write this Hamiltonian where E is the sum of the annihilation operators, and then we can find the equations of motion simply. And when we look at the averages or expectation values, we can write these in terms of not the operators, but complex variables. And by taking the discrete time Fourier transform, where theta is the angle around the resonator, we can find this mean field equation, which is called which is a damped and driven nonlinear Schrodinger equation, and we often call it the Lugiato-Lefebvre equation. Okay. So after this, I'm going to jump to our results. Our approach will relies on using a high quality optical microresonator. We pump it with two lasers. The two lasers create a very clear discrete time translation symmetry in the system. And when we look at photon count probability in the system, and this discrete time translation symmetry will be spontaneously broken as a result of the interaction of the photons, which generates solitons in the cavity. And then we show that this platform is very useful for demonstrating large DTCs, DTCs carrying defects, and also can be used for observing phase transitions. Apart from our demonstration, which appeared on arXiv a few months ago, there's a highly relevant result from the University of Hamburg. I believe Andreas Hammerich would present on this the same conference here, and they use an atom cavity system. Now, one of the experimental tricks that we use in our demonstration is self-injection locking. Self-injection locking is essentially the locking of the laser to the cavity mode, and that happens when we do not use an isolator between our laser and our microresonator. And as a result, the light pumped from the laser into the resonator would be backscattered into the laser cavity as a result of Rayleigh backscattering. And that essentially what happens is that locks the laser to the mode of the cavity. Okay? Now, when the laser also generates a microcomb, it will also lock to the microcomb, and then the laser essentially works as an arbiter between the cavity mode and the micro mode, and that results in very stable frequency combs. And one of the very important practical benefits is that we can get soliton formation in a deterministic and turnkey fashion, in the sense that usually when we want to get to soliton state in these systems, we have to sweep the laser, but without sweeping and with simplifying the system by removing the isolator, we're able actually to get these solitons in a turnkey fashion. We turn on the laser as I've shown here, we get the state, we turn it off, we lose the state again, turn it back on, we get it, and the cycle can continue. Which was demonstrated in an integrated platform recently as well. An interesting story is that this technique was used by the industry player in the field of microcombs for a while before academics realized its potential. It was essentially a secret sauce of the industry that came into academia. Now, we go beyond pumping with one laser. We go to pumping with two lasers. We lock them simultaneously to two cavity resonances and also to one microcomb. And that confirms our theoretical predictions from 2017 and 2019. From there, let's take a look at the experimental setup. We have a whispering gallery mode resonator, which is prism coupled to the two pump lasers. The two lasers are separated by an integer multiple of the repetition rate of the cavity, which is the inverse of the round trip time, the time it takes the soliton to go around for one full cycle. And then when we have shown that this process can be described by a modified LLE, modified Lugiato-Lefebvre equation, with a periodic drive. Let me emphasize this drive term again here, which possesses a clear symmetry in terms of both the slow and the fast time. So we talk about the fast time tau. It's like the propagation distance z in the context of fiber solitons. And it's proportional to the theta coefficient. Now, let's see how this discrete time translation symmetry can be broken in the state. Where, for an example, I'm showing here m equals 5. Without soliton generation, we have a periodic background, the lattice, which is generated by the beating of the two pumps. And when a soliton is generated, we go from periodicity TR over 5 to TR, which means 5 time multiplication by a factor of 5. And we have noticed that this particular case is very robust, as I will explain in a few slides. So going from m equals 5 to m equals 8, we'll see that we have a larger variety of possible period multiplying states, for instance, 2T1 or 4T1 or 8T1, where T1 is the periodicity of the state. And when you compare that with m equals 5, you see that we have more variety. And there are also possibilities of getting states which are not symmetry broken. For instance, the bottom right I have shown here, we get one soliton in every lattice trap, and that means the symmetry will not be broken. For the temporal evolution of these pulses, which are shown at the bottom, the temporal evolution is shown at the top, where the dark red lines are the peaks of the solitons. You see that we have observed evolution in a stable fashion over hundreds of cavity photon lifetime and thousands of cavity round trip times. And when you look at the frequency spectrum, the characteristics of harmonic generation is very clear between the two pumps, in these cases marked by two red arrows. And then the hyperbolic secant envelope is also clear, as shown here by the red dashed line. Now, jumping to the experimental results, we looked at m equals 4 and m equals 3, and we observed very good matching between theory and experiment. We observed also that hyperbolic secant envelope. And then to make sure that we are dealing with a COM or mode-locked frequency COM, we look at the so-called RF signal, radio frequency signal, which is the beating between adjacent harmonics. The blue curve on the top left shows the beating between the two pumps, and the red curve shows the RF signal for the subharmonic generated, which is, you see, almost 1/3 of the first one. And both of these signals are very narrow, have very small phase noise, and that is a signature of a calm or stable frequency COM. Now, taking the Fourier transform of the numerical data, we find a numerical waveform for the generated state. And based on the discussion I had and the examples I showed earlier, we see that it is indeed, in both cases, they are indeed period multiplying states. Now, in this system, it's possible to observe the equivalence, temporal equivalence of solid state physical concept of defects. We have vacancies. It's a point defect when you have a missing atom. Here we are missing a soliton peak. We also have dislocations, essentially misplaced soliton peak, and also interstitials, like a pulse appears where it shouldn't be. Going beyond that soliton formation regime and the regime of looking at self-injection locking, we also looked at the regime of modulational instability, which is a regime in which the harmonics are generated from parametric gain and they rise from vacuum fluctuations. The example shown here is for a case of m equals 18. So the two pumps are 18 FSRs away from each other. And 3 FSR spacing between the subharmonics shows that we can realize a 6D state. And this is a result from 2019. We also looked at the stability of the state in various initial conditions were used with random initial powers. We see that the final state is very reliably produced. And we also looked at the addition of noise to the system. As you see, the signal to noise ratio on the right panel shows that when it reaches 10 dB, which is very easily achievable in experiments, we get highly reproducible and repeatable generation of the final time crystal state. There are some relevant results in the literature, theoretical, and also some results, including experimental results in fiber resonators, which we believe are very closely related and should be able to show similar results. Now, future directions, particularly what we are pursuing, is a demonstration of controlled phase and transitions, meaning we generate different DTC phases controllably and we transition between them. Also are interested in showing larger sizes of DTCs, but as you see, it's possible to sweep the frequency of the laser and demonstrate in principle large DTC sizes.
5 minutes.
Thank you. The large degree of the high degree of coherence, temporal long-range order in these systems can be used for applications requiring coherence, large coherence times. Can also be used for some photonic applications, for instance, frequency division with high stability, and more importantly, for two-point stabilization of narrowband combs, which cannot be used with standard techniques such as the self-referencing. And when we essentially stabilize the two-pump lasers by coupling them, by locking them to external transitions, for instance, atomic transitions, we can improve the stability of the system significantly. Similar demonstration, of course, using external broadening of the pulse appeared in 2018. Of course, there were significant differences, but that tells us that this platform indeed has the potential to demonstrate what we're looking for. So in summary, we've demonstrated DTC formation in a dissipative system, in a nonlinear photonic system, and we have looked at some of its defining signatures and the importance. One of the important advantages of using this system is that it can leverage the well-developed platform of nonlinear photonics and a lot of optical techniques which have been used in the same way that quantum optics was useful 30, 40 years ago and still is. And we have talked about some of its applications. With that, I'd like to thank my friends and colleagues who have contributed to this work. In particular, Krzysztof Sasha and Andrei Matsko have been very helpful in clarifying and developing some of these ideas. My colleagues at OE-Waves, my former colleagues, particularly Utmaleki and Wei Liang, have been supportive, highly supportive of the experiments, and I've also benefited from many exciting conversations with Tobias Herr. With that, I'd be happy to answer any questions, or you can reach out to me via this email here. Thank you very much for your attention.
Thank you. We have time for one question again, or two. please shout. I mean, everything was pretty clear, and there was very nice presentation, but maybe somebody
Thank you.
didn't understand something. Okay, I guess that you will be. Oh, Shane Kelly would like to ask question. Please do. Please unmute Shane Kelly.
Yeah, there we go. Yeah, no, I was wondering if any of the light can be squeezed. If you get any squeezed light in the cavity, and
Yes, it's possible, and it's been demonstrated. Squeezed lights, squeezed states of light have been demonstrated in microresonators before, particularly by Avik Dot at the, I believe, Michal Lipson group. They were at Cornell before; they're now at Columbia.
do you know if that will affect the stability of the time crystal, or?
Not sure if they use, I don't believe they use self-injection locking, but in principle, the level of stability we get is about like simply on the order of hours with DTC. So with temperature control, the states we get are very stable. And I believe in those states we can have the same level of stability, if not better.
Okay, thank you. And Vincent will have a last question.
Yeah, thanks so much. Exciting talk. I'm quite intrigued by the multiple factors of the periods, like 5, 8 times. So I was wondering, what the role does the interaction play to the multiplication of the periods?
Would you please repeat the question? So I think I did not
what
hear
does
part
the role of the interaction play in setting the period of the district time crystal?
Okay, I think you're asking about the role of something in
the interaction. Part of the interaction. Yeah. So I was wondering how the interaction plays any role in the emergent period of the time crystal that breaks the time the translational symmetry in a discrete way, right?
Okay. Yeah. So you see, without the Kerr nonlinearity, which governs the interaction of the photons, there will be no soliton formation. Essentially, the reason we get the sidebands and the reason we get their synchronization, as we have shown, is the Kerr nonlinearity between the photons.
So will the interaction strengths change the period?
It will not change the period in the sense that the beating between the two pumps will fix the number of pulses, the maximum number of pulses we get. So it generates essentially a lattice trap around the resonator, and then they will be locked. The solitons will be locked in those positions. There is some playground, but it's not a lot of freedom.
Okay. Thank you. Thank you, and thank you, Hossein. And we have to move to the next talk. The next talk will be given by Igor from. Well, I don't know, Igor. Is it Nottingham or Tübingen, from where you will give the talk? Because you seem to be in some coherent state. So Igor Lesanowski, he has the floor.
Jakub, thanks a lot for the introduction. And while I'm trying to share the screen here, let me also just thank the organizer for giving me the opportunity to present our work. I'd much rather be in Trieste right now. So I will get to your question, Jakub, in a second. I have a slide there. But first, I'd like to talk about the title of the presentation, which is on time crystal phase transition fluctuations and quantum correlations in an emitter waveguide system with feedback. It's rather lengthy, I admit, but I hope I will be able to explain all these terms to your satisfaction. And concerning, my state of being, let's say, I've moved in 2019 from the University of Nottingham to the University of Tübingen, and my main place is now at Tübingen, but I have a part-time position in Nottingham, and of course I'm very happy to be able to collaborate with the people there. Also, Andreas Nullenkamp, as I understand, is giving the talk tomorrow. He is now there. And of course, time crystal related work I've been doing in the past has been done together with Juan Garahan, Matteo Macuzzi, and Filippo Gambetta. And what I'm going to talk about now has actually been done by Federico Carollo, Giuseppe Buonaiuto, and Beatriz Olmos. Good. This is the outline of the talk. It's on open quantum systems and the realization and analysis of stationary state phases and also transitions into time crystalline phases. So what I will do, and a lot has been said already in this conference, I will very briefly tell you about how to formulate the system, discuss very briefly the master equation, but then focus a little bit more on a new aspect that I want to talk about here, which is how to include feedback and how feedback can be used to actually control the dynamical phases of such a many-body quantum optical system. We'll tell you a little bit about waveguide quantum optics, because this is the system that underlies the physics that I'm going to talk about. Tell you a little bit about how interactions come about, what sources of dissipation there are, what is nice about these systems, and we'll also tell you that in the end, the system can be actually very nicely described in terms of collective observables, which allow a very nice and actually exact treatment of the system in the thermodynamic limit. I will then look at the dynamical phases, show you the phase diagram, look at fluctuations, and also finally at spin squeezing, and conclude with a summary and an outlook. All right, so what's the basic setting that we are dealing with? Well, I said already, it's open quantum systems, and in an open quantum system, we have a system of interest. Oh, this is not good. I want to switch to the pointer. We have a system of interest, and this is embedded in a bath. And now what the system does, it exchanges quanta with the bath. And what we can also do, of course, is we can now detect what is emitted into the bath. I mean, simple example are, for instance, atoms that interact with the electromagnetic field. Atoms can decay from their excited state under the emission of a photon, and this photon can be, of course, detected. And depending on the detection, we can now change the parameters of the system through some kind of feedback construction. And this is the basic idea of the setting that I want to consider here, and in which we analyze some time crystal-like dynamics. So the basic idea is to detect what has been emitted, and in our case, this will be photons, and conditioned on the emission, we will control the parameters of the system such that some interesting physics, some interesting states appear in the stationary regime. All right, so how do we formulate this? And this we have seen now a number of times already today. The workhorse here is the Lindblad master equation that describes the evolution of the density matrix. And there are two parts to it. So one is the coherent evolution here, represented by this commutator term. It's just a von Neumann equation, essentially. And then we have here this term that accounts for dissipative irreversible effects, and this whole let's say agglomeration of operators here is also usually called the dissipator, that then depends on the jump operators Lj. And just one thing I want to say, because it becomes of relevance on the next slide. So one term here that one can single out in this dissipator is the so-called quantum jump term, which basically, in an unraveled picture, where you think not in terms of this average dynamics, but in terms of trajectories that you can then average to get the density matrix. In this kind of picture, this term would correspond to quantum jumps that the instantaneous state of the system undergo. All right, so just a basic example to bring this kind of closer to something tangible. For instance, if you look at a very simple situation where you have just a two-level atom that is subject to a coherent drive, you would, on resonance, so you would write the Hamiltonian as something that is proportional to the sigma x Pauli matrix, which just coherently changes the state from the low-lying level to the high-lying level at a rate that is given by this Rabi frequency omega. And then you would have, for instance, in competition with this coherent excitation, incoherent decay from the excited state to the ground state at the rate kappa, and the corresponding jump operator would then be, in this case, just square root of kappa times sigma minus, where sigma minus is simply the operator that takes the excited state to the ground state. So now feedback, and I want to make this very brief. A, I'm not an expert, and B, the time is also limited. So I will start from a feedback scenario that I think is probably the simplest and easiest to grasp. And it very much relates to the system that I just showed you on the previous slide, namely in a two-level atom, or in general, an ensemble of atoms that undergo spontaneous emission events. And once there is such a spontaneous emission event, then the atomic ensemble will release a photon, and this photon can be detected. And now you see, for instance, if you have this detector and you record the sequences of clicks over time, then you would see something like this. So every stroke here corresponds to the detection of a photon emitted from the atomic ensemble. So in one very simple feedback protocol that one can do, and please take into account that I'm a theorist here, is that after each detection of photon, I perform an immediately unitary rotation on the state of my atomic ensemble. And what that would entail is just in the master equation, a simple change of this quantum jump term that I mentioned on the previous slides. So where you just see, well, what happens is that I have my state rho before the detection, then the quantum jump takes place. So that means I have to apply L dagger and L on the respective side. And then you see I apply a unitary transformation, a unitary rotation on the state of the system afterwards. And you see in a very, I would say, transparent and pictorial way how such a feedback protocol based on photon counting would work. This is not what we are doing here for the purpose of this work. In this work, we consider something that relates to homodyne detection. There one does not count the photons, but one actually monitors continuously in time the electric field amplitude of the emitted light field from the photons. So you can do this. I don't want to go into details here, though there are lots of experiments that have demonstrated this. And also, if you now implement this kind of feedback strategy, and the book by Wiseman and Milburn, for instance, will tell you how this can be done in practice, then you will see that such a feedback protocol will, let's say, do a little bit more to your master equation, not just change the jump operators, but will actually introduce additional terms, not only in the dissipative jump part, but also in the Hamiltonian part that describes the coherent evolution of your system. So our protocol is such that we say, well, we detect this photocurrent that is corresponding to the electric field of the emitted photons. So you can write down an expression for this photocurrent x of t, which is kind of the expectation values of expectation value of some operators of your systems times plus noise plus some noise. So this is a noisy quantity. It has a deterministic part and a noisy part. And depending on the value of this amplitude x, we change the amplitude or the Rabi frequency of the laser field that drives our atomic ensemble. So, and the corresponding strength of the feedback is regulated by this parameter G. So if you take this and accept this, so we measure the signal here, and depending on what we measure, we change the strength of the Rabi frequency with which we drive the atomic ensemble, then you can write down your modified master equation, and what you will find are terms to that effect, where you get an extra bit here that depends on to your Hamiltonian, that depends on the feedback strength, and also here on the actual structure of the photocurrent that you're measuring. So this is very pictorial. I show you, so to say, the precise operational structure of the situation that we are considering in our work. And what you also have is that you modify the jump operator. So what you see is that jump operators get shifted also by an amount that is proportional to the feedback strength G, and also by something that corresponds to the operator that you're effectively measuring. You are measuring effectively by monitoring this photocurrent. Good. So this is the idea. We perform this homodyne detection scheme on our atom waveguide system, which I haven't explained yet, and this will change your Hamiltonian and the jump operators, and this will result in something interesting. So now let's jump to the system that we are interested in applying this strategy to. And this system is just formed by a waveguide, so-called nanofiber, for instance, and next to it sits atoms that are nicely lined up in a regular chain. So this is not something we made up, but this is really some system that is under active investigation in a number of labs worldwide. So foremost, maybe to mention, is the group by Arno Rauschenbeutel at the Humboldt University of Berlin. But there are, of course, many, many people who have contributed to developing not only the experimental side, but also the theoretical understanding of the system. The dynamics of the system can be modeled again in terms of a master equation. And again, we have a Hamiltonian here, and this Hamiltonian consists of some kind of laser driving term. You have seen this before, and here the lasers might not necessarily be on resonance. You can also have a detuning. So then you have another term that amounts to the effective interactions between the atoms, because you see what happens here in such a system is that the atoms actually emit photons into the guided mode, and then you see, for instance, that when a photon is emitted by this atom 2 here, it can be propagating to the right, and then it can be absorbed actually by the atom at position 3. And by this, you effectively create an interaction between the atoms along the chain. Then the next term that we want to discuss here in the system is of dissipative nature. So this is actually the very nice point about the system, that you have due to the fact that your atoms interact with this waveguide and emit into the waveguide modes, you can very nicely, let's say, attach detectors to the left and to the right, and very efficiently resolve photons emitted from this atomic ensemble in this waveguide. And of course, once you have detected those photons, you can then apply your feedback strategy. So this is very neat, because this setting naturally gives you, let's say, a reduced set of modes, very similar to an atom cavity setup, that allows you to apply this feedback strategy in a very controlled way. And last but not least, what we also have in principle is, of course, not only emission into the guide of the atoms into the guided modes, but also, of course, emission of photons from the atoms into free space. But I can tell you already, for the purpose of this talk, we sweep this under the rug, and will pretend that this decay channel can be suppressed sufficiently well. So, of course, it's nice that we can write down this master equation that faithfully describes our atom waveguide setting. But for the purpose of the work that I'm going to present on the time crystal, I'd like to simplify the situation a bit more. And first of all, I told you already that I do not really want to consider emission into unguided modes. I really want to pretend that the system is built such that all the photons that are emitted incoherently from the atoms end up in one of the two guided modes, either emitted into the right or into the left propagating direction. What I also assume is that the atomic positions are commensurate with the photon wavelength. So that means the distances between the atoms are multiples of the wavelength associated to the transition on which the photons that I detect here at the end of the waveguides are emitted. And once I do this, this whole complicated looking master equation acquires a much simpler structure, which we're even going to simplify more in the next step. So you see, we have here the laser driving, and with the Rabi frequency omega, and this laser driving is only dependent on so-called collective operators, which, by the way, also then in this setting capture the incoherent decay into the guided modes. And this is actually important because this collective nature of this excitation of the atoms and the collective nature of the coupling of the atoms to the dissipation allow a very simple and very nice to study structure of the system. So what I will do in the following is also consider a situation where I do not have any detuning and I do not have any interactions between the atoms, which is actually something that sounds complicated to do, but it's not. Yeah, so this is actually a generic situation. So when the emission rate into the left guided and the right propagating mode, when both emission rates are the same, then you can show that under those conditions where the atomic positions are commensurate with the wavelength of the emitted light, you effectively have no interactions because the atoms happen to sit at positions with respect to each other such that the interaction with the light field interferes away. So now in this very simple setting, we really have a simple Hamiltonian. So this is essentially non-interacting Hamiltonian, and we have this kind of collective jump operator. We want to apply feedback. And this feedback that we want to apply is very similar to the one that I discussed before with the detection of the photocurrent. So to say, if you want to know more precisely what you measure, we are measuring the so-called P quadrature. This is kind of measuring the electric field, which you, of course, can decompose into an X and P plane, just measuring it in a particular angle, namely along the P direction in this quadrature representation of the electric field. So if you want to forget what I just said in this talk so far about the experimental motivation of this system, you can do so right now, because now is the part where we start the theory. Because with all these simplifications and with all these assumptions that I just laid out, we finally end up with an equation that we can analyze. And so applying the feedback strategy to the system, which is composed of the atoms and the waveguide, and measuring this P quadrature, you find that the master equation is modified in a way that you add in your Hamiltonian part interactions that are proportional to the feedback strength, G, and you also modify the jump operator that accounts for the emission of photons into the right propagating waveguide mode. Why the right propagating waveguide mode? Because this is the mode on which output we perform this homodyne detection, which then controls what we feedback into the system. Just for comparison, if you look at the decay term at the dissipator corresponding to emission of photons into the left propagating mode, this is not modified. This is just a J minus term. It's just a kind of normal collective jump operator that you would write down. Whereas here you have this modification, which is also involving here the feedback strength G. So now what's nice here, and I already said this in passing a couple of slides back, is that this whole master equation here now just depends on collective spin variables that you can write, for instance, like this. So it's just a sum over all local spin variables that are represented by these Pauli matrices sigma k in the respective directions alpha equals x, y, and z. So this is nice, because this allows us to perform a treatment that is actually becoming exact in the thermodynamic limit. That means when the number of emitters, number of atoms tends to infinity. What one can then show is that actually the magnetization operators, which are just these operators here, these collective spin operators, but divided by the number of atoms, that these operators in effect become classical, which means that their commutator tends to 0. And in this limit, the mean field description of our system dynamics, and I will just show you the corresponding equations on the next slide. So in terms of the expectation values of the magnetization operators becomes exact. Just note that in order to do this in a meaningful way, so that one has a well-defined limit, one has to also scale the decay rate, so the emission rate of the photons into the waveguide accordingly. So it has to go down as 1 over n as the number of particles n increases. So this is just to ensure that there is a consistent and meaningful thermodynamic limit. But once you do this, you can actually now arrive at a set of 3 coupled mean field equations, which just tell you about the time evolution of the magnetization components expectation value of mx, my, and mz. And just I want to say, so this is of course very, very reminiscent of these boundary time crystals that Fernando Iemini is going to talk about this afternoon in the other session. So this is just for you also to build a connection here between this talk and Fernando's. So looking at these mean field equations, we of course can now analyze those. And I just want to tell you that I just reparameterized here these equations slightly, that instead of taking this feedback strength G, I introduced this parameter kappa, which is equal to 2G plus 1. This is simply because with this, the structure looks a bit more pleasant and more compact. But anyhow, so and you have done this for sure when you're listening to this talk and you're a theorist. Once you have mean field equations, things become really nice and pleasant because you can start analyzing them and play around with them. And you can, for instance, draw a stationary state mean field diagram. So this is just obtained by putting the left-hand side of these equations to 0. There are some conserved quantities, which I don't want to talk about here. But if you consider this, then you find a phase diagram here as a function of the strength of the laser driving and the feedback strength. And what I plot here is the order parameter is just a Z component of this magnetization operator in the stationary state. So, and you see here 3 phases. One is a stationary phase. So this is a plot here now performed as a function of time in this at the position of this square. And you see the dashed line is the mean field solution, and the colored lines are the exact solutions or the numerical solutions of the master equation. And you see really, as I kind of promised, as n tends to be large. I mean, 50 is still far away from infinity, but at least you see the trend that this is really approaching this mean field result. More importantly, and this is connecting now to the topic of this workshop, is this emergence of the time crystal phase when you increase the driving of the atoms. And you really also see very nicely that you have these persistent oscillations here, and that when you compare this with a numerically exact finite system results, that these finite system results, of course, also show oscillations which are damped as expected, but that the amplitude grows the larger the number of atoms becomes. And
5 minutes.
Yes, thanks. I'm getting there. And what you can also do is you can now really look along this cut, and you see these different regimes. You see here the time crystal phase where the average magnetization is 0. You can look at the scaling of the damping gap. You see here in this phase, in the time crystal phase, it goes as 1 over n. So the larger the number of atoms, the more persistent these oscillations become. And then at this transition point, you see the scaling changes in between the stationary and the time crystal phase. And you see the scaling with 1 over square root of n. So the last 3 minutes, just hope there will be some questions. I will just spend on going beyond this mean field approximation, because I think this is actually the interesting part about this study. So what we were looking at in order to go beyond the mean field is to analyze the dynamics of fluctuation variables. And these fluctuation variables are just defined as 1 over square root of n times the angular momentum operators J, So these macroscopic spin operators minus the expectation value. And you find that when you write down the anti-commutator of these fluctuation variables, then you get out the covariance matrix of the macroscopic spins. So now if you look at the commutation relations and you take the equations of motion for our system, when you look at the equation, at the commutation relations between these fluctuation variables, you see, okay, the matrix on the right-hand side is not one that you would associate, so to say, with canonical commutation relations of a certain class of degrees of freedom. But in fact, you can change this when realizing that, in fact, this matrix can be rotated, or the system can be rotated. And you find that the system can be rotated in a way that from these three operators that are parameterized by alpha equals x, y, z, one operator becomes classical, that we call the z component, and the other two operators are fluctuating perpendicularly to it. So this rotation can be accomplished analytically. And what you then find is that in this plane, orthogonal to this classical direction, you see that these fluctuation variables actually behave like position and momentum and obey the canonical commutation relations. And this immediately makes you wonder, well, let's see what the quantum state is, and characterize it in terms of squeezing. Why squeezing? Well, you know, if you have these canonical conjugate variables, they obey a Heisenberg uncertainty principle. And what would be nice, for instance, in the context of, let's say, quantum enhanced measurements, is to see whether you can actually generate a stationary state that shows squeezing, where one direction here in this plane of fluctuations has lower variance than you would typically expect for let's say a non-squeezed state or a classical state. And this is what I want to wrap up here in the last minute with. You can analyze this squeezing here, and you find indeed that now when you do the phase diagram, that there's no squeezing in the time crystal phase, and actually these fluctuations here grow as a function of time. But what you find is that one of the stationary phases, and not the other one, in fact, is a phase where you get squeezing at stationarity. And this is interesting, I think, because if you think about the system, so in principle, you can integrate it. You don't have to use atoms, let's say, that are sitting in free space next to this fiber. You can, in principle, implement such a system maybe with impurities or quantum dots next to a waveguide. And you can also, of course, apply this kind of feedback strategy in principle. And just by applying this simple feedback, you can not only realize this, for us, interesting time crystal phase, but probably you would be able to also create some kind of correlated matter on demand, for instance, such squeezed phases, which could be well important for technical applications like in metrology. And this is just the idea. So we like this model because it's to a large extent analytically solvable. And of course, if one really wanted to implement this in a practical setting, one would have to ask some questions about how long-lived are these phases really, because, for instance, due to the effect of the emission into unguided modes. But this is something we are really keen on exploring together with experimentalists. And this brings me to the end of the talk. Here's some other works of our group that we have produced in the past year. Thank you very much for your time. I hope there are questions. Thanks a lot.
Thank you very much. And Odette, please unmute Odette. Yes, he is unmuted. Please ask the question.
Thank you very much, Igor, for the very nice talk. I have a question about the noise squeezing that you commented on in the end. So in the time crystalline phase, you expect to get period doubling bifurcation. So you should have actually two solutions, and you're supposed to look at the fluctuations around one of them.
Mm-hmm.
And then, so my question is, are you looking at truly the covariance around the attractor, or when it explodes, is it because of activation by noise to hop to the other attractor?
So, okay. I have to process the question because I mean the language is really very much orthogonal to what I'm used to. But let me pick up maybe this last comment on noise. So I mean, noise is not present here, right? I mean, it's all deterministic evolution in this framework that we are using to describe the dynamics. So therefore, I don't think that this is related to noise. So in the sense that you talked about when you're speaking, for instance, about activation. So what I would really see the connection here with, I mean, it's in essence what you find is that if you have your macroscopic spin, what you can do is you can identify a classical direction, and then you can essentially create bosons perpendicular to it. I mean, it's a bit like the spirit of Holstein-Primakov, but okay, I think our approach is a little bit better, yeah, and better controlled than what you would obtain when applying this Holstein-Primakov approximation. I'm not entirely sure whether I answered your question, though, to be entirely honest. Yeah.
So I mean, actually, when you do a Holstein-Primakov, you are getting a fluctuation Hamiltonian around your attractor, which is good, right? It tells you how your system would respond if you kick it away from that attractor.
Yeah.
And now, technically, when you look at the covariance, you would actually look at the statistical, correlations between these fluctuation operators that you added on top of the attractor, and this would be what you drive with noise, actually.
Okay.
So, hence my question.
Well, I still have to process it. Okay. So.
Okay. Yeah. No. Okay. So I mean, if you want, we can discuss.
Yeah. No. Thank you very much. Yeah. So, but okay.
I guess we shall move to our host Rosario, who also wants to ask question, and so this will be the last question before coffee break. I hope that the organizers will provide coffee. Rosario.
Sure, of course. I'm not sure if this is related to Odette's question. You at some point it was written that fluctuation grows in time, growing time.
Yes.
Does it mean that there is any stability, or I just missed this point?
Yeah, I think this is a good point. So I think it was written and I brushed. I don't open the slide now. So what I said is when you look at the fluctuations in the time crystal phase, then you see you have oscillations, or at the squeezing, let's say. Yeah, if you look at the squeezing in the time crystal phase, then you see it fluctuates, but it also oscillates, but it also drifts away. And I think at some point this is certainly becoming artificial, right? But what it means is that in the end you just spread out in your XP plane, in this description that we are employing indefinitely.
But this means that the reference point is not a good one anymore, because you're expanding around something, but you're drifting away. I don't know if I understood correctly.
So
this way.
So when it comes to the precise interpretation, I would not know now from the top of my head what to say here, but to be fair, we didn't really pursue this investigation further because this was not the interesting point to make about the squeezing, so to say. Yeah. So I mean, for let's say characterizing the squeezing in, let's say, the useful regime, it's not the time crystal phase that we were interested in, but this stationary phase, this squeezed phase. Yeah. And well, when approaching to the boundary of the time crystal phase, there, this choice of coordinate system, let's say it like this, seems to be the appropriate one. But with this same choice in the time crystal phase, it seems that one has to think whether this is a wise thing to do. Yeah.
Okay. Thank you.
Okay. Thank you all very much. I think that we deserve our coffee, and we meet again in 21 minutes at 4:30. Thank you, and see you then.
Hi.
Hi. Okay, I just wanted you to unmute and everything is fine. So we are waiting.
Okay. Thank you.
Okay, it is almost.
Okay.
So we still have to wait a little bit, maybe 1 minute more.
Okay.
Okay, I think we can start the last session of today. So Albert Cabot will tell us about, surprisingly, some new subject, time crystal. The floor is yours. Albert?
Okay, thank you. First of all, let me, yeah, can you hear me?
There are problems.
Can you hear me?
We can hear you, but with some...
Can you hear me? With... You don't hear me well?
We hear you well. Let's try, okay?
Okay, okay. Okay. So let me thank the organizers for the opportunity that I've done in collaboration with Jean-Pierre and Robert Stambling. And it is a work about dissipative time crystals in which dissipation plays a key role. We have that the interplay of dissipation, interactions, nonlinearities, and driving leads to the breaking of time transfer symmetry. And these have different ways. We can have discrete time crystals. In this context, we have the system described by a time-dependent master equation, and the master equation is periodic in time. And in the thermodynamic limit, there emerge there are observables that display decaying oscillations, and the fundamental period of these oscillations is a multiple of that of the master equation. And then we can have also continuous time crystals in which the master equation is time independent in some frame. And again, there emerge non-decaying oscillations, but now the crucial difference is that the period can vary continuously with the parameters of the system. And these are some works in which these ideas are studied. So let me focus more in detail in this limit, this n to infinity limit, in which spontaneous time symmetry breaking occurs. So if we have a spin system, this is the infinite spin limit. However, this phenomenon can also occur in zero-dimensional systems, like nonlinear optical cavities. And in this case, it would correspond to the infinite photon or infinite excitation limit. Let me also add difference with our interactions, as well as these zero-dimensional nonlinear bosonic systems. In this limit, their dynamics is given by classical nonlinear models with 3 degrees of freedom. And for this reason, in this reference, the notion of emergent semi-classical time crystal has been introduced. And in this sense, the results that I will present will belong to this category. So let me talk about entrainment. So entrainment is a type of synchronization phenomena in which a self-sustained oscillator adjusts its oscillation frequency to that of an external periodic forcing or to a fraction or multiple of it. So this is an example. So we have 2 signals. In blue, the one of the self-sustained oscillator. in red the one of the forcing, and we can see that in absence of synchronization, both oscillate at frequencies which are not commensurate. However, there is a dynamical regime in which the oscillator can adjust its frequency to half of that of the forcing, and this case is known as superharmonic entrainment. So there is the interesting question of whether this kind of synchronization phenomena can be observed in quantum systems and in the quantum regime. And this is a question that has been addressed by a lot of people in the past 10 years. And these are some of the basic questions. So whether these phenomena survive quantum fluctuations, which are the signatures and indicators, whether there are genuine quantum aspects, etc. And these are some references. Now, a very important system in the context of quantum synchronization is the quantum van der Pol oscillator. And here I have to acknowledge the talk by Marco Shiro, in which he has nicely introduced this kind of system. So these are some important references. And here I will focus on the squeezed quantum van der Pol oscillator, which is a model known to display superharmonic entrainment. So basically, this is the model in the laboratory frame. So we have a master equation for a driven dissipative bosonic mode. And basically, we have a term that gives energy, a pump, and a nonlinear damping. And recall, this is the definition of a dissipator. And then we have a Hamiltonian in which there is the squeezed forcing that introduced a discrete time periodicity in the model. So we have that it has this frequency. And this frequency is in general different to that of the oscillator. So a nice thing is that we can define a rotating frame in which this model becomes time independent. And in general, in this talk, I will be showing results in this frame. So in this rotating frame, I indicate by the subscript R, the dissipative part is the same, but now the Hamiltonian is time independent. And instead of the intrinsic frequency, we have the detuning. Okay, and of course, both frames are connected, laboratory and rotating frame are connected by a unitary transformation that changes the Hamiltonian and the state of the system. So a nice thing about this rotating frame is that the master equation can be written in terms of a time-independent Liouvillean. And we can try to understand the dynamics of this system by analyzing the spectral properties of the Liouvillean. And this is something, the spectral properties of the Liouvillean is something has been introduced already in the talk by Anna Sampera and also by Marco Shiro. So basically, the Liouvillean has a set of right eigenvectors, a set of left eigenvectors, a set of eigenvalues that appear in complex conjugate pairs and whose real part is non-positive, and there is at least one stationary state. So a nice thing of the model I discussed is that it displays a parity symmetry. That is, the master equation is invariant under this transformation. Or more formally, we can define the parity superoperator, which has two possible eigenvalues, and the consequence is that all these eigenmodes are either parity symmetric or parity antisymmetric. And in particular, the stationary state is parity symmetric. Now, I said that this time symmetry breaking phenomena occurs in certain limit. In our case, this is the infinite excitation limit. So we define this parameter n, that is the gain strength over the nonlinear dissipation strength. So in the limit in which this parameter goes to infinity, basically the boson number diverges. However, the rescaled quantities tend to a well-defined quantity. And this well-defined quantity comes from the mean field equation. So this equation for this complex amplitude is derived basically factorizing the equations of motion for the amplitude, and it has two free parameters, the detuning and the squeezing strength. So basically, we can understand the mean field dynamics by studying the bifurcation diagram, and this system displays just one bifurcation at this critical point, and below this squeezing strength, the stable attractor of the dynamics is a limit cycle. It's a time-dependent solution with this fundamental frequency, and above this critical squeezing strength, the stable solution, the stable attractor, are to be stable fixed points. So back in the laboratory frame, this limit cycle, the frequency is generally not commensurate with that of the forcing. So in this regime, in this dynamical regime, there is no synchronization. Whether in this above the critical point, in this dynamical regime, the bistable solutions require this kind of harmonic evolution. And we find indeed subharmonic entrainment with that external forcing. So a bit, this is what I aim to do in this talk. So we have seen that we have two dynamical regimes at the mean field level. The limit cycle regime is associated to a lack of synchronization, and the bistable regime to entrainment. And I want to discuss whether at the master equation level we find continuous time symmetry breaking or discrete time symmetry breaking. And I will do so analyzing this limit, that is the infinite excitation limit and the long time dynamics. And to do so, it's a good way to do so is a finite size analysis of the Liouvillean spectrum, since we can write the state of the system at any time in terms of the eigenmodes of the system. And the eigenvalues, the time dependence enters through the eigenvalues and this exponential form. And from here, we can obtain any observable. So two possible interesting outcomes are non-decaying oscillations if in this limit the real part of the eigenvalues of some eigenvalues goes to 0, while the imaginary part is different from 0. And we can also have dissipative phase transitions and multiple stationary states if some of these eigenvalues go to 0. So let me first analyze this regime below the critical point. So this is the lowest lying Liouvillean eigenvalues for different ends. So we go from left to right towards the infinite excitation limit. So in the horizontal axis, we have the real part of the eigenvalues, and in the vertical axis, the imaginary part. And we can already see from this picture that there are two groups. A set of eigenvalues, which in this limit, the real part saturate to a finite value, while there is another set of eigenvalues, which in this limit, the real part tends to 0. And we can analyze this in more detail, and we can ask how this real part vanish. And they turn out to vanish following a power law with n. And this is what I show here. So I show the real part of the 8/1 of these eigenvalues, and we can see how as we increase n, this is in log scale, all of them follow one of these power laws. Moreover, the imaginary part tends to multiples of that mean field frequency I presented. So basically, this is conceptually what happens in this limit, in this regime. So in the long time and in the infinite excitation limit, basically many eigenmodes with non-zero frequency but 0 decay rate contribute to dynamics. At finite n, what we will observe is that oscillatory quantities such as the amplitude dynamics or two-time correlations display oscillations with increasing lifetime as we increase and as we go to the infinite excitation limit. So in this case, we find in the regime continuous time symmetry breaking. So let's now focus on the other regime. So in this other regime, the behavior of the eigenvalues is very different. So basically, we can already see that the leading eigenvalues are real, and all of these saturate to a finite value in the infinite excitation limit, while this shows the interesting behavior of going to 0. So basically, in this regime, we find the closure of the Liouvillean gap, that is a dissipative phase transition. So basically, above the critical point, this eigenvalue goes to 0. And this is what I show here for 3 different values of n. So above, for squeezing strength above the critical value, we basically see how this eigenvalue changes trends and goes very fast towards 0. And the larger is n, the closer this happens to the bifurcation point, and the faster it goes. And a very important point is that the eigenmode that goes to 0 is parity antisymmetric, which is different from the stationary state. This is what I already said. So in red, this is n, and in red we have this eigenvalue that goes to 0, while in blue we have the other eigenvalue that we see that saturates to a finite value as we increase n. So basically, a very important consequence of this gap closure is that due to the antisymmetry of this mode, there is a spontaneous parity symmetry breaking. This means that we can define these two states, which are stationary states in this limit, and which, because they are made of two states of two modes with different symmetry, they do not have a well-defined parity symmetry. So we can ask who are these symmetry broken states, and if we compute the amplitude in these symmetry broken states, it tends towards the mean field amplitude of the bistable solutions. So these parity symmetry broken states that we find are a reminiscence of the mean field bistability. So for finite n, they are not completely stationary, but they have a very long lifetime. And this is what I show here in the amplitude dynamics. So starting from one of these parity broken states, we see that as we increase n, the lifetime increases dramatically. And this is in log scale. So which is the relation of this with discrete time symmetry breaking? So for this, we have to go back to the laboratory frame and analyze the dynamics of the state. So I will write down the dynamics of the state in the laboratory frame, and in particular at stroboscopic times. That is, at times that are multiples of the period of the Hamiltonian. And why is that? Because at the stroboscopic times, we can write this state easily in terms of these rotating frame eigenmodes, which is what I've been explaining before. So basically, we know that we have a set of parity symmetric modes and a set of parity antisymmetric modes. And basically, the parity symmetric modes contribute the same in both frames at stroboscopic times. However, the parity antisymmetric modes acquire an oscillating sign in the laboratory frame. And this is the key feature. So basically, if we have the closure of the Liouvillean gap and the mode implied in this closure is antisymmetric, we have that this is equivalent to discrete time symmetry breaking in the laboratory frame. And this is because due to this eigenvalue tends to 0, basically the long time dynamics in the laboratory frame can be written as this. And we have this contribution for this from this parity antisymmetric eigenmode, which has an oscillating phase, which comes from the fact that it is antisymmetric. So now we find that the dynamics of the state displays period doubling. And due to the symmetry of this mode, we find that only the parity antisymmetric observables are sensitive to this period doubling. So let me end up, yes. So I will end up with, well, showing what I said for this dynamical regime in these pictures. So basically the main result in this regime is that the gap of the Liouvillean closes. This is related to discrete time symmetry breaking, and basically in the rotating frame, we find these symmetry broken states that show a diverging lifetime. And you can see this here. And if we look at the dynamics in the laboratory frame, we will observe, as I said, period doubling. So for instance, here I show the amplitude dynamics, and this is a zoom of this region in the laboratory frame. And in blue, we have the full time evolution. In yellow, the stroboscopic time evolution, and time is given in units of the period of the Hamiltonian. And very clearly, we can see this period double dynamics, which even for finite n, far from this infinite excitation limit, it seems almost stationary. And recall that any antisymmetric observable will be sensitive to it. So in conclusion, in this regime, we find discrete time symmetry breaking. So the main result here is that the squeezed van der Pol oscillator can be regarded as an emergent semi-classical time crystal in which we can have both continuous and discrete time symmetry breaking depending on the parameter values. And importantly, the transition from one kind of time symmetry breaking to the other is a dissipative phase transition with parity symmetry breaking. So I hope these results will be shown in the archive with these additional results, and I will be happy to answer to your questions. So thank you for your attention.
And do we have questions? We have time for a question. Okay, there is a question coming from Oded.
Yes.
Hi, Albert. Thank you very much. So your bifurcation,
yes,
does it actually occur exactly the same point that you have the exceptional point, or are they displaced from one another due to the fact that you have dissipation in your problem?
Okay, so so I guess you refer to this additional result. So
yeah.
Well, you can find that the classical bifurcation point is manifested in the Liouvillean as a spectral signature, and you find that the critical, and this is the exceptional point, and you find that the critical squeezing strength at which this exceptional point occurs tends towards the classical critical point when you do this infinite excitation limit. And this is maybe, you can maybe appreciate it here. So this turning point turns out to be an exceptional point. And as you do this limit, you can see how, I mean, I can show with more detail how this turning point approaches the classical bifurcation point. I don't know if that answers your question.
Yes, I guess it does. But do you make this this getting closer to the point by reducing the dissipation? Actually, you take the zero couple limit.
Well, the n to infinity limit is the corresponds to making gamma 2 over gamma 1 very, very small. Nevertheless, dissipation, I mean, you can never kill dissipation, because actually nonlinear dissipation is what stabilizes these attractors when there is an instability, right?
I see. Okay, thanks.
Okay, thank you. And thank you, Albert.
Okay.
And we now switch to Fernando Iemini from Brazil.
Hi, can you hear me?
Yes, we can hear you.
Okay, okay, let me share then my screen.
Very good. And we see.
Okay, can you start?
Okay.
Okay, so first, let me thank for the organizers for this very nice conference on time crystals. And also, I thank for the opportunity to participate and present these recent works that we have on boundary time crystals. So I'm Fernando Iemini. I am from Institute of Physics from Universidade Federal Fluminense in Niterói, Rio de Janeiro, Brazil. And this recent work, it's called Boundary Time Crystals in Collective D-Level System, and it was done in collaboration with Luis Fernando dos Prazeres, Leonardo da Silva, and myself, and both from the same institute here in Rio de Janeiro. And we just uploaded a few weeks ago on the archive. If someone is interested to take a more careful look, just go to this link here. So just a brief outline of this talk. I'm just very briefly comment on this concept of boundary time crystals that was introduced a few years ago, and then I go directly for my results on these collective D-level systems. And in particular, we are going to analyze in more details the D equal 2, 3, and 4 cases, and then I go for my conclusions and perspectives. So the idea of these boundary time crystals, it was introduced in this work in 2018 with other collaborators. Many of them are here: Angelo Russomano, Marco Schirò, Rosario Fazio, and also in collaboration with Jonathan Keating and Marcello Dal Monte. And the idea of this boundary time crystal was looking for ordered time crystal phases. Instead of the full Hilbert space with all of its degrees of freedom, but just in a macroscopic portion of this full system. So the idea was to focus on the analysis of the dynamics just at the boundary of the system. And by the boundary, I just mean a part, but a macroscopic part, in order that we can properly define a phase there, and look for spontaneous symmetry breaking on these boundary degrees of freedom. So just to mention very briefly, this idea, it comes somehow from the surface critical phenomena, that we have different examples where only at the surface of my system, that represents a macroscopic portion of my system, it is ordered, while in the bulk we don't have any ordering. And we are looking not for the ground states or thermal states of my full Hilbert space, but on non-equilibrium dynamics that go directly out of the no-go theorem here. Just a second. So the idea then is that we have the full Hamiltonian. It just described by the part of my boundary degrees of freedom that they're just that we call this blue spins. And I have also the bulk Hamiltonian degrees of freedom that are just the blue one. And the full Hamiltonian is just the boundary term, the bulk Hamiltonian, and an interacting term between both of them. But we are only be interested in the dynamics of my boundary system. And in order to analyze the dynamics of my boundary system, we know that the full Hilbert space, it's just driven by the Schrödinger equation. And if you trace out the bulk degrees of freedom, we have it's always possible to define an effective description for my boundary degrees of freedom that is always described by a completely positive trace preserving map. So in case that we have some ordered time crystal phase or a boundary time crystal phase appearing in my system, it means that I have a macroscopic order parameter such that the expectation value of this order parameter in the thermodynamic limit of both bulk and boundary degrees of freedom, it has some non-trivial time dependence, or a time dependence that's different from the Hamiltonian time symmetry itself. So we would have this dependence that persists only in the thermodynamic limit and would be also robust to some perturbations in order to characterize our boundary time crystal phase. So a very simple example of a model showing this phenomenology is just looking for, instead of looking for very intricate or hard to analyze CPTPM maps, we just look for a Markovian system such that the effective dynamics is just driven by a Lindblad master equation. And in particular, if you look for just collective two-level systems coupled to a cavity, we can see this boundary time crystal or this kind of phenomenology appearing in a very simple form. We know that there are many other different examples of Lindblad master equations showing the dissipative time crystals also, as was presented in this work. But in this particular work and in this talk, I'm just going to focus on collective systems. So for this type of dynamics, we just have a competition between a coherent dynamics that is just a field, a collective field applied along the x direction that tends to flip my spins in my system, and a competition of a collective dissipation that tends to make a collective decay on my spin degrees of freedom. So I just represent this type of Lindbladian or this type of collective dynamics here in this rough, let me say, it's a rough schematic representation where we have a competition between a coherent Hamiltonian of this collective level 0 and 1 and the collective dissipation between these two. It's going to be easier to show the other models that I'm going to present in this schematic representation here. And then for the specific model here, it was shown that if the dissipative part is too strong, it's stronger than the coherent dynamics, we don't have any non-trivial time dependence of macroscopic observables in the long time limit, and the spins just tend to be a ferromagnetic trying to point down in my system. Otherwise, if we have that dissipation is smaller than the coherent dynamics, we see this boundary time crystal appearing in the system. So we see that while for finite sizes, we see some oscillations of the magnetization with finite decay time. But as we increase the system size, we see that this lifetime increase also until if we go to the thermodynamic limit, we have this persistent oscillations of the magnetization. So one of the models that I'm going to analyze here, show here in this talk, is exactly this collective two-level system, but we are going to take a more careful look on different interacting terms on the Hamiltonian, just like SX, SX, or Z magnetization interactions, as well as a magnetic field along the Z direction. We're going to see that they have different effects on my boundary time crystal in more details in a few slides. So with basis on the insights that we have on these collective two-level systems, I'm also going to analyze a collective four-level systems that is just defined as a pair of interacting two-level systems. So then the system, it's locally, it is very similar to this collective two-level system, but we also consider a collective interactions between these two pairs of collective two levels, and we look for the dynamic phases that appears when we have interactions between these two boundary time crystal phase. And actually we see that some more rich phases appear there, and that is very interesting. And as a third model that I'm going to discuss in more details in a few slides also, it's this collective three-level system, where now we have this, that each one of my subsystem has three levels, so we have this collective three-level system, and each one of these pairs of collective levels here, we are going to consider that they have dissipative dynamics or Lindblad dynamics, very similar to the boundary time crystal for the two levels. So in this case here, we have somehow a competition between a pair of two-level Lindbladian channels. So we have this Lindbladian acting in this first two, and this Lindbladian acting in the second two collective channels. And different phases also can appear in the system. It's just worth recalling here that even though this is similar, it resembles similar to the four-level collective system in the sense that we might have a pair of collective two levels, but this is not the case because these two pairs here, they share a common collective level. So the full algebra of collective operators that drives the dynamics here is actually an SU3 algebra that cannot be decomposed as a pair of SU2. So this is just because they have some overlap in one of the collective levels, and different physics can then appear in the system. So first, just looking for the simplest case, that is the two-level collective system. And for a moment, I'm just focused on the interacting terms, on the effects of them without the magnetic field along the Z direction. So in order to analyze the system, we go directly to the macroscopic limit, since we know that if you want to look for the collective magnetizations in this macroscopic limit, we can use a semi-classical approach that gives us some reliable results. So the semi-classical approach is just defining a macroscopic magnetization, and we close at the second cumulative expectation values. With this closure, we obtain an effective Heisenberg picture for the magnetization dynamics, and they have this very peculiar structure from which we can also see some symmetries in the dynamics that comes from this dynamical equations of motion. One of them is just the conservation of total spin. That is really the one, even for finite system size. We have the Lindbladian is a collective operator. A second symmetry is that we see that in the X and Y dynamics for the magnetization, we see that the magnetization along Z, it has somehow a factorization structure. And then we see very easily that we have also a reversibility symmetry by inverting the time and the magnetization along the Z directions. The dynamical equations remain the same. And as a further peculiar property of this dynamical equation of motion, we also have some quasi-conserved quantities. And I'm saying here quasi-conserved because since they are defined with this logarithmic of magnetizations between the three different axes, this logarithm is just defined up to integral modulus of 2 kappa pi. So this very peculiar dynamics here, and if you look for different effects of the interactions, we have somehow the same this general view for what happens in my system. So I'm just looking here for the phase portrait in the phase space variables where the x and y, they define the momentum variable here. And Q is just the magnetization along the z directions. So we have this general picture for the dynamics that if we have some initial conditions that have a larger momentum, we have some attractors appear in the system or some repulsors that appear in the system, and we don't see really the time crystal dynamics in the system. However, if for certain initial conditions with small p and close to magnetization equals 0, we see several closed orbits appearing in the system. So this closed orbits is really the boundary time crystals appearing in the system. And we see that for the specific model, it always appears having a fixed steady state or the steady state as a center or with magnetization equals 0. So when I say here that is a center, it's just looking for the stability of the steady states here located at mz equals 0. And we see that from a Jacobian stability of the steady states, they have purely imaginary eigenvalues and do not have any real term. So looking then from this perspective of Jacobian stability, we can actually take a look at the full phase diagram for different interactions along z and along x direction. And we characterize this phase diagram of the model with the presence or absence of boundary time crystal just from the stability of the steady states or fixed points of the dynamical equations of motion. So in this case, we just define this tree vector here, and where the first element is just the number of centers like this that appear in the phase diagram, and n single hyperbolic and pair hyperbolic is the number of tractors that do not have non-trivial time dynamics. And we see that as we increase the magnetization along x direction, it tends to increase the number of centers, thus to have more boundary time crystals appearing in the system. While if we increase the magnetization, the interaction of the magnetization along the z direction, it tends to destroy some of the center or some of the boundary time crystals in the system. And then now looking for the effects of the magnetization along the z direction, we see first that this magnetization, it breaks the Z2 Hamiltonian symmetry. And in order to understand the effects of it along the phase diagram of the model, we just look again for the stability of the steady states from the Jacobian of the system, where the effects of this perturbation can be seen as this 3×3 matrix here. And from perturbation theory for general non-Hermitian matrix, we find that the first order corrections for all of these center steady states that used to characterize the boundary time crystal, they now have a real part, which means that or they become attractors or they become repulsors. And in this way, they always destroy the boundary time crystal ordering. So in this sense, a magnetization that breaks the Z2 symmetry of the Hamiltonian tends to break all of this boundary time crystal in our system. So with this, I'm sorry?
4.5 minutes.
Okay, so let me just run a bit more fast. So for this four-level collective model, we take we consider magnetization along x direction, but also consider magnetization along z direction in both of my pair of two-level systems, and also some collective interaction between these two pairs here. So now we have SU2 algebra, and the following equations of motion that are similar, but now we have some interactions between the two systems appearing here or here also. And the idea here will be to consider more general phase in the sense that we break all of those dynamical symmetries of the two-level system in order to generate some more complex dynamics, but also possibly with richer dynamical phases. And for this reason, we consider, for example, that kappa is equal 1, so we have weak dissipative regime for each local two-level system. So have a strong omega x and omega x such that they would generate the boundary time crystal. But we put also some local magnetization in both of these two that we know that destroy the boundary time crystal. And then study the effects of this hybridization of these broken time crystals when we increase the interaction along the z direction between them. And we see that indeed for omega zeta zeta equals 0, it's just a trivial phase, no boundary time crystal, just looking for the magnetization along the z direction. If we increase above some threshold, we see some limit cycles appearing in the system. Further increasing the interactions, we see some period doubling oscillations in my system, where I see that it has now 2 minimums during the periodic oscillations. And further increasing, we see a chaotic dynamics appearing in the magnetization or in my phase space. So in order to have a more general view of what is happening due to this interaction along the ZZ direction of this pair of collective models, we just look for the orbit diagram from my system, just looking for the minimums along that dynamics of my magnetization. And we see that while for omega ZZ close to 0, it's a trivial state, no dynamics at all in the long time limit. But then we have a transition to a limit cycle phase here around 0.2. And if you keep increasing, and then just this figure here is just a magnification of this upper figure here. If we keep increasing the interaction, we see this series of period doubling verifications up to chaotic region. So indeed, to consider this more general for a level collective system, we see richer dynamic phases appearing there, from ferromagnetic steady states, limit cycles, chaotic dynamics, and the further three cycle periodic windows appearing here in between the period doubling verifications. And then for this third model that we analyze, as I mentioned very briefly, is just the collective three-level system, where now we have a coherent Hamiltonian just along the x direction, coupling each pair of collective level, and dissipative decay happening also in each one of this pair of collective levels. And we want to analyze essentially the competition of these two Lindbladian channels acting in the first pair and the second pair of my system. So I'm just to recall, as I briefly mentioned, that since they share a common collective level, we cannot reduce this just to interacting collective spins anymore, because we have a more general SU3 algebra that cannot be reduced to this case. And then for simplicity, I'm just going to show here the case where both omegas 1, 2, and 2 and 3, they are equal, as well as kappa 1, 2, and kappa 2, 3, they are equal as well. Then we want to study the effects of the competition between these two channels, the delta parameter, and the ratio between omega and kappa if they are in the strong or the weak dissipative regime. And we will obtain the following phase diagram for this type of model. It's very interesting because we see these three different phases along also with a critical line separating some of these phases. And one of the interesting things that we see is that as long as delta is different from 0, but smaller than half, so even a small competition of these two first levels to the second two levels, it tends to have a trivial phase in the sense that we destroy any boundary time crystal that could be appearing in the system there. So the dynamics, it tends to cancel a collective level, the level in the middle here. In the end, it's going to be like a dark mode without any population, and it stabilizes a static steady state just between 1 and 3rd collective levels. So another interesting thing that we also see is that a boundary time crystal appears in the form of limit cycles for larger coupling competition delta, and also omegas over kappa larger than 2/3. And it's interesting from the point of view that we see that the boundary time crystal here, it's appearing even for the strong dissipative case, that we know that for just two levels, this will be just a trivial phase. So somehow this competition enlarges the space or of support for a boundary time crystal. And also this critical line separating these three different phases here, it's very interesting because in this specific line here, we see boundary time crystals appearing there, but with the coexistence of both closed orbits, just like the two-level collective system, but also with limit cycles, depending only on the initial condition that we start the evolution of the system. And moreover, if you look for the Lyapunov exponents of this dynamics, we see that in both this case of closed orbits or limit cycle dynamics, they have a full degeneracy of null Lyapunov exponents. So all of the Lyapunov exponents are equal to 0. So just to be specific, more clear here. So here is just consider the initial conditions that are close to the fixed points, and we see these closed orbits. So the continuous and dashed lines, they are for different initial conditions. But if you start with initial condition that's far from the steady state, from the fixed points, we see these limit cycles. Both of them lead to a 0 Lyapunov exponent. So with this, I just go from a conclusion that in this work, we analyze the boundary time crystals in 2, 3, and 4 collective levels. And we see that depending on the dimensionality of these collective levels, these boundary time crystals can appear in different forms, providing a richer phenomenology for this phase. And as interesting questions, there are many different, but I would just mention, would be interesting to analyze larger D levels, as well as take a more careful look on this global and dynamical symmetries for this phase. So with this, I thank for the attention. Sorry for if I passed too much the time.
Thank you for your talk. And Odette has one fast question. And then we get a fast answer. Odette?
Sorry, it seems that I'm the only one awake. But I was only clapping. If you want, I can ask a question. So there is technically in the conference until now, there is a nomenclature that I think all comes to be the same. And I wanted to verify that you agree with me. That we have heard people talk about the Liouvillean eigenvalues. We heard people talk about the complex pole dynamics in Green's function responses or spectral functions of the responses. And you talk now about null Lyapunov exponents, and there was, of course, mention of exceptional points. Would you say that your null Lyapunov is what people would call exceptional points?
I don't know, actually. I don't know.
I would say
I'm sorry.
Yes. I would say that yes, but okay.
Okay, so with this doubt, we shall pass to the last talk of this session. Sorry, Lincoln, we have to move on. And the talk is by Professor Das, right? So he can share the screen. Paraloid, are you there?
Yes, sir, I am there.
Okay, good. So we have to change the screen slowly.
Now I can share.
Okay, very good. You can share your screen. And the floor is yours, or the screen is yours, or whatever. The microphone is yours.
Okay. Firstly, I want to thank the organizers for giving me an opportunity to give a talk in this interesting conference. I am Praloy Das from Indian Statistical Institute, India. Now, the title of my talk is the Cosmological Time Crystal, that is the cyclic universe with a small cosmological constant in our toy model approach. Now, I would like to acknowledge my supervisor, Professor Subir Ghosh from ISI Kolkata, and all my collaborators, Dr. Supriyo Pan and Dr. Prabir Pal from India. Now, this talk is based on our work, this one. The plan of my talk is that I will give a brief introduction, then I will talk about the classical time crystal. After that, I will discuss about the non-commutative action was derived by Fabi, Hans, and Stern. And then I will discuss about the cosmological time crystal, where we'll see that it will allow us to give a cyclic universe with a small cosmological constant. And finally, I will summarize it. Now, within a few years, time crystal has created an enormous amount of interest, both in the theoretical and experimental context. Now, the symmetry of a system is broken when the ground state of the system is less symmetrical than the equations of motion that control the system. Now, the time crystal is borrowed from the familiar crystal that has specially ordered structure in its ground state, and it is a manifestation of breaking of the continuous translation symmetry, leaving behind a ground state with the discrete translation symmetry. Now, the question posed by Shapere and Wilczek is the following: was that can a system with time periodic ground states that breaks the continuous time translation invariance exist? Now, the resulting system with the discrete time translation symmetry was referred to as the time crystal. Now, after that, a mathematical model for a classical time crystal was provided in this paper by Wilczek, and later a more physical model was constructed where the relevant degrees of freedom undergoes the periodic Sisyphus dynamics in its lowest energy state. Now, what we have done in our work is that we have applied the concept of classical time crystal proposed by them, and which is we have applied in an extended model of Friedman-Robertson-Walker cosmology, that means the FRW cosmology. Now, this extension is induced by the non-commutative gravity contribution with an underlying quantum gravity perspective, which was derived by Fabi, Hams, and Stern. You can see this paper. Now, two of our main results is that the scale factor, it borrows the Sisyphus-like periodic behavior that characterizes the classical time crystal, but for more interesting, it serves as a physically motivated toy model for a cyclic universe. And also the minimum energy state or the ground state consists of a condensed leading to an arbitrarily small positive cosmological constant. Now, it should be noted that that our model is purely geometric in the sense that no matter degrees of freedom are added from the outside. Now, let us discuss the classical time crystal. Now, first, we consider a generic Lagrangian. The Lagrangian looks like of this expression that leads to the energy of this type. Now, we have rewrite this energy as this type of form where we have seen that this energy minimizes at phi 0 dot equals to plus minus of root over of a by 3b, and phi is equal to phi 0. Now, this is the classical time crystal ground state with mutually opposing requirements of simultaneously constant velocity and constant Poisson. Now, to further understand this situation, we note that the Lagrangian equation of motion looks like this expression for phi double dot, which diverges at the energy minima, and furthermore the energy becomes a multi-valued function of momentum. Now, this momentum p curves at the energy minima of del p by del phi dot as equals to 0, where we get phi 0 dot equals to plus minus of root over of a by 3b. Now, we'll see that this curve structure leads to catastrophe for our cosmological time crystal model. Now, at exactly ground state, the system becomes singular, but the interesting behavior is recovered for the system being close to the ground state with some energy being slightly above the minimum energy. That means E is equal to E plus minimum plus delta, but delta is very small. Now, we assume this energy is occurs at the phi t. We can solve for phi dot, and from this expression we get the phi expression for phi dot, and this equation has 4 independent solutions, and we interpret this behavior of the system as that phi dot tends close to square root of a by 3b, but it gets altered by the second term. But since also this term cannot go beyond a certain value, since phi cannot be exceed phi t. Now, although the Poisson changes, but when it reaches near about the value that minimizes the potential, the velocity falls back, and this cycle is repeated. And in short, this is called the Sisyphus dynamics. And thus, the system is forced to undergo Sisyphus dynamics, where on an average phi stays close to the constant phi 0, but periodically goes through a phase of non-zero phi dot as phi 0 dot. And now we come to the part of the non-commutative action. Now the conventional effort of Friedman-Robertson-Walker metric reads like this one, where A is the scale factor. Now we have taken the non-commutative corrected FRW metric that was derived in this paper, where x mu and x nu as the component of only theta mu nu is non-zero, and this is the non-commutative parameter. Now this is the expression for the metric, where c is the velocity of light here. Now the generic form of the Einstein-Hilbert action is reads like this one, where r is the Ricci scalar r minus 2 lambda root over of minus g d4x, and it reads like of this expression, where the non-commutative corrections are introduced via theta in these numerical parameters: sigma, beta 1, beta 2, beta 3, alpha 1, and alpha 2. Now we have just written this action in a more compact form, and in the compact form it looks like this expression, where A, B, and C takes up this type. Now we have introduced a dimensionless universal parameter nu as of theta square lambda square by c to the power 4, and we have defined that the canonical momentum P is a del L by del A dot, and from this expression of momentum we get our theorist expression for the Hamiltonian. Now in this work, this Hamiltonian constitutes our primary result, which we will now study from the classical time crystal perspective. Now a very richer curve structure is revealed from this P versus H diagram. Now following the paper of this one, we have the plot of P versus H shows that because of the A dot 6 term, which was present in the del P by del A dot. I am just going to the previous slide. This one, we see that this is the fourth order equation in A dot and having 4 solutions. Thus, this dotted blue line, it resembles the profile of this paper, which was posed by Shapere and Wilczek, where the A dot 6 contribution is negligible. Whereas this solid line, deep green line, this shows the new structure with some significant A dot 6 contribution. Now we name this new structure as the battering catastrophe that reduces to the Salottel catastrophe as obtained in this paper, where the contribution of the A dot 6 term becomes negligible. And also this curve structure is completely washes out if the A dot 6 term dominates even slightly, leaving an inverted symmetric V-shaped diagram with vertex at h equal to 0. Now we come to the part of the cosmological time crystal. Now, firstly, we'll consider our model where we will not consider the A dot 6 term. That means it's the planar model without the A dot 6 term. Now, from the action, we can find out the Lagrangian equation of motion. This is the Lagrangian equation of motion, where A prime is just the derivative of A with respect to the scale factor A. Now, in this figure, we have plot the scale factor A, its time derivative A dot, and the total energy H. Now, this solid line shows the scale factor A, and this dotted line shows the A dot, and this dash dot curve shows for the Hamiltonian for our system. Thus, we can say that the cosmological model framed by the time crystal, it allows the cyclic nature of the universe. Now, we believe that some further investigation is still required to possibly understand the nature of entropy transfer from one cycle to another during this evolution of the universe. Now we follow the elegant route of this. Just we have followed this paper, and that shows that the way of removing the singularity by introducing a regulator in the form of mu. We have just introduced the regulator mu in a Lagrangian, which looks like this expression, where fx and gx looks like of this one, and k and the quantities k and j are of this type, which depends on a and b. Now from this Lagrangian, we have derived the Lagrangian equations of motion, and these two are the equations of motion. Now, although this model is similar to that of the model by Wilczek from the time crystal point of view, since they have also only a dot square and a dot 4 terms, and we have just neglected the a dot 6 terms for our present case right now. And however, the scale factor dependence is much more complicated in our case, and this is reflected in the X profile that contains both the positive and negative values. Whereas for their case it has only either positive or negative values, but for our case it has both positive and negative values with the sharp edges separated by some smooth curves. Thus our model describes a double Sisyphus dynamics. Now this is the profile of the scale factor A. This one is for X and this one is for the Hamiltonian. Now we will come to our model where we will consider the a dot 6 terms. Now from the action we have similarly we have as previously derived, we have calculated the equations of motion where a prime, b prime and c prime denotes the derivative with respect to the scale factor. Now a very surprising and interesting result is that we have found some small parameter window in which the scale factor oscillates smoothly without any singularity and with constant energy, which indicates also again a cyclic universe. So this is the profile of the scale factor A. This one is for the X and this one is for the H. Now similarly, we have tried here also to construct the mu regularized model, what we have done in the previous one. We have kept the same form of the Lagrangian as we have taken in the previous one, but with here the forms of F and G are new. Okay, we have taken new expressions. And from this, since the Lagrangian is the same form, we will find the same set of equations of motion as we have previously derived, but with some new identifications with this expression. But this shows that the regularized form for a dot 6 model is not entirely satisfactory, as it fails to generate the independent form of C, which was given in the action. This suggests that a more elaborate version of the mu regularized model is needed to faithfully represent this a dot 6 model. Now we'll come to the point of the time crystal where we have derived the cosmological constant with small cosmological constant in our model. We have let us derive the condensed energy where we'll need this condensed values A0 and A0 dot, which will minimize the Hamiltonian. Now the Hamiltonian can be written in the form of this. We have just written from the Lagrangian one. Here V effective looks like of this expression. Now here the Hamiltonian will be minimized for A0 dot of which looks like of A0 by 6 B0, where A0 is obtained from the potential of derivative of the potential with respect to A at A is equal to A0. Thus, the ground state energy will looks like of this expression where A0 and B0 are the forms of A and B, where the scale factor is A is equal to A0. Now, this is the figure which shows the qualitative evolutions for the variation of the effective potential. That means the solid line shows the del V effective by del A, and the cosmological constant is shown by the dotted line, and the Hamiltonian is shown by this dashed line. Now in this figure we see that this solid line, it starts the A-axis at A0, which is incidentally greater than A equal to 1. That means it is in future, where we define the effective cosmological constant as this expression, where we can see that the value of lambda at A0 is equal to lambda effective, which can be arbitrarily very small, as we see from the figure, with even a large value of lambda. Thus, the value of cosmological constant gets renormalized in a sense. Now, lastly, I will summarize what we have done in our work. We have proposed a new form of time crystal, and some of its consequences have been studied. The model is a generalization of the Friedman-Robertson-Walker cosmology, which is endowed with some non-commutative geometry corrections. We have found that the scale factor undergoes the time periodic behavior or the Sisyphus dynamics, which allows us to interpret this cosmological time crystal as a physically motivated toy model to simulate the cyclic universe. The other major success of this toy model approach is that it allows us to generate an arbitrarily small positive cosmological constant in a natural way. Now, in future, we would like to see that here we have since our model is purely geometric in sense that no matter degrees of freedom are included. So matter degrees of freedom can be the area where it can be looked. Since where one can conjure that more than one time crystal structures, that since the behavior will coming from the matter sector as well as the FRW sector. Now another interesting part is that we can analyze the other forms of time crystal that can appear naturally in cosmology, in particular in FR gravity, and in also some higher derivative gravity theories. Thank you for your kind attention.
Thank you very much. And we have time, unlimited time for questions. Krzysztof Sacha wants to ask the question, so he can unmute himself.
Yeah, yes, sir.
Okay, I have a question because in your Lagrangian or your Hamiltonian, you have kinetic energy part and also potential energy part. And in order to solve the equation of motion, you have to, I guess, you have to introduce some regularization parameter. I guess that this is in a similar way, like in a work by Al Shapere and Frank Wilczek. And then do you have some, because in Shapere and Wilczek work, it is possible to show that this effective model can come from the two-dimensional physical model. And then this, as far as I understand, then this regularization parameter appears naturally. Can you justify your regularization parameter in your model?
Yeah. Now, in our model, from the Lagrangian, we have find out this equation of motion, and then we have to regularize this. What they have done in their paper, we have just followed that route and introduced mu. Here, mu is the regulator which we have introduced in this Lagrangian, and from this Lagrangian, we have found out the equations of motion, and when we have plotted this, and we see that this model also describes some compared to them, our model describes some double Sisyphus dynamics.
But what is the meaning of mu?
Where is?
What is the meaning of the parameter mu?
Value.
There is a mu parameter. Mu,
yeah, mu in the Lagrangian.
Yes, but what is the meaning of this parameter? Do you have some physical meaning in your model for this mu, or this is just a regularization?
No, this is just a parameter regulation, and I can also say that what we have for the plot, what we have given the value of mu is something like 10 to the power minus 5 6. Just a value. This no
meaning. Okay, thank you.
Okay, thank you very much. I don't see other questions, so I think thank you very much, Praloy, and
thank you.
And we have reached happily the end of the session. The ship has reached the harbor, so we can safely go home or go to the conference dinner. I don't know if Rosario has some dinner prepared for us in traditional Italian style.
Well, this is something we should still work out and find out how to do.
Yeah,
but,
okay, good.
Okay, meanwhile, so thanks a lot for sharing the session. I think we meet tomorrow morning at 9, right, Christoph?
Right, yes.
Yes. Okay, see you tomorrow. Bye-bye.
See you all, guys. Thank you very much. Bye-bye.
Thank you.